Chapter 25 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 25. The Romance of the Tides. The ceaseless ebb and flow of the ocean has from the earliest ages attracted the attention of all thoughtful observers of nature. The waters of the sea are never at rest. No sooner is the ebb reached than the flood begins. No sooner is the flood reached than slowly but surely the waters begin to ebb. Thus for ages, ever since the world was first formed, the waves of the ocean have beaten on the shore, and since scientific speculation and research began, the cause of the tides has attracted the attention of men of science. The study of the tides belongs to the realm of astronomy. To many this statement doubtless comes as a surprise, yet it is strictly true. The tides are due to the gravitational pull on the earth of two celestial bodies, the sun and the moon, and the waters, as the most easily pulled portion of the earth, are consequently the parts which are most displaced in position. The moon is chiefly responsible for the tides, although the sun plays a smaller part in the phenomenon. Notwithstanding its vast superiority in size, the sun is so far away that its pull on the waters is much less than that of the insignificant moon. Our satellite plays the chief part in raising the tides, but the sun certainly makes its influence felt. Every month there are 2 spring tides and 2 neap tides, as they're called. The word spring tide is somewhat misleading, for a spring tide has nothing whatever to do with the season of spring. Spring tides, the highest tides of all, are due to the fact that at that time the moon is either new or full. The sun and moon are both exerting a pull in the same straight line, and their combined force raises a higher tide than usual. The lowest tides, or neap tides, take place when the moon is at first quarter or last quarter. At these periods, the sun and moon are tending to pull the waters in different directions, and the resulting tide is lower than the average. The tide which is raised on the earth is made up of 2 parts: the direct tide, the tidal wave on the portion of the earth towards the body which raises it, and the opposite tide on the other side of our planet. As the earth rotates on its axis from west to east, the watery bulge, as one astronomer calls the heaping up of the tides, appears to travel from east to west as a tidal wave twice in 25 hours, or to be more correct, 24 hours 48 minutes, the time required by the earth to make a complete rotation relative to the moon. Of course, the waters of the ocean do not travel around the earth, only the form of the wave travels from east to west. This wave originates in the deep waters of the Pacific Ocean and travels westward, its speed varying with the depth of the ocean. The deeper the waters, the faster the velocity of the wave. As the wave is in motion, it meets other waves, so the resultant wave is not so simple as might be supposed. In about 12 hours, however, the main wave reaches New Zealand, and in about 30 hours it arrives at the Cape of Good Hope. Here it joins 2 other waves, the tide in the Atlantic off the African coast, and a reversed wave from the other side of Cape Horn. The resultant wave travels through the Atlantic with a velocity of about 700 miles an hour. In the deep oceans there is little bodily motion of the waters. The waters merely rise and fall with the velocity varying as their depth. It is otherwise, however, near the coasts. At the mouths of great rivers, the waters move bodily up the river beds, similarly on the seashore, as indeed we know well from experience. In the mouths of some rivers, the result of the rising tide is very picturesque. In the case of the Seine, the tide surmounts the current of the river and rolls with increasing velocity up the river bed. This phenomenon is known as the bore. At Côte de Bec on the Seine, this phenomenon is especially noticeable. The following lengthy notice by the master hand of Flammarion is worthy of quotation, so well does it explain this remarkable spectacle. Quote, "On the day and the hour indicated, the wharf, shaded with perennial trees and splendid walks, is crowded with spectators. These are the inhabitants who are never tired of the grand spectacle of the river transformed, and strangers who come from far to enjoy and to study it. For a long time before the arrival of the flood, impatient eyes search the horizon, and the less experienced think every moment that they see it beginning at the extremity of the bay which forms this bend of the Seine. A low murmur announces its approach when it is still at a distance of several miles. The vast sheet of water advances rapidly under a radiant sun, in the midst of a verdure which a zephyr scarcely stirs. There are all the motions, all the agitations, all the fury of a tempest-tossed sea. Very soon the spectacle changes to become grander and more singular still. The enormous wave, which marches at the head of the tide, swells, rises, stands up. It bursts of a sudden, and its summit falls with a crash. An immense roll is formed and unfolds itself, sometimes from one end to the other. It is a cascade which moves, which runs and remounts the river with the speed of a galloping horse. The flood runs along like a wall of foam, overthrowing all obstacles and rearing itself up each instant like a gigantic plume, to fall again quivering on the bank which it deluges. The ground sometimes trembles under the feet of the spectators, who see in less time than it takes to describe it, the boiling mass passing on and pursuing its ungovernable course." End quote. In England there is another famous tide which rushes up the Bristol Channel with a tremendous force. The greatest tide in the world, however, is to be seen at the Bay of Fundy. Here the Atlantic passes into a lengthy channel, with sides which gradually converge. As the water rushes up this channel, it becomes heaped into a great volume, of which the height at the spring tides is over 50 feet. In mid-ocean, the rise and fall of the waters is much less than round the coasts. The island of St. Helena, for instance, is washed by a tide of which the height is only about 3 feet. Wonderful are the phenomena of the tides at the present time. Mighty are the forces possessed by the rolling waters. But a scientific study of the tides reveals facts more remarkable than those which we have mentioned, truths vastly more astounding, which give us a glimpse into the past of our world and enable us to forecast its future. The mathematical study of the tides was commenced by Sir Isaac Newton, who confirmed by his work the vague notion of Galileo and Kepler that the tides were caused by the sun and moon. Laplace, the famous French mathematician, completed Newton's investigation and worked out mathematically the complete theory of the tides. In more recent times, the mathematical work of these investigators has been supplemented by that of Professor Sir George Darwin of Cambridge, whose researches have given us a glimpse into the shadowy past and the mysterious future. Darwin found, in the course of his investigations, that the constant tidal wave, persistent throughout the ages, acts on the earth as a brake acts upon a machine. It tends to retard the earth's motion of rotation on its axis. In other words, the tides tend to increase the length of the day by slowing down the rate at which our world is spinning. It will be noticed that, so far as we know, this is the tendency of tidal action. In the history of mankind, the day has not lengthened by even a small fraction of a second, and we do not know from experience that this constant tidal action is wearing down our planet's speed. Nevertheless, mathematicians have proved this to be the case. Millions of years are required for the results of these forces to become manifest, so it is not surprising that the length of the day has not changed appreciably in the course of the few thousand years during which the human race has lived on this planet, and the few hundred years in which astronomers have determined the length of the day with any approach to accuracy. Not only is the day becoming longer, the moon's distance is becoming greater, and its period of revolution is increasing in length. At the present time, our day is about 24 hours long, and our month about 27 days. Darwin's researches show that with the constant friction of the tides on the earth, the day will be lengthened at a more rapid rate than the month, and in the distant future the day and month will coincide in length, both lasting for 55 of our present days. The moon will revolve round the earth in exactly the same period as our planet requires to rotate on its axis, so that the two bodies will perform their revolution round the sun, as if united by a bar turning the same face to each other. This is the future which the continuous action of the tides holds in store for our planet. Not only does a study of tidal action give us a glimpse into the future of the Earth and the Moon, it also enables us to read the past, when the Earth was in a plastic condition and tremendous tides were raised not in the oceans but in the semi-liquid crust of our planet in the early stages of its history. According to Darwin, the Earth in the remote past was rotating on its axis in a very short period, probably between 3 and 5 hours. Reasoning backward, we see that the Moon must have been much nearer to the Earth at that time than it is now, and was probably revolving round its primary in a period identical with that of the Earth's rotation. The Earth and the Moon, then in a gaseous or semi-gaseous condition, must have been revolving almost in actual contact. This was a state of affairs which could not continue. The condition of the Moon resembled that of an egg balanced on its point. The Moon must either recede from the Earth or fall back on its surface, and had the month been even 1 second shorter than the day, our satellite would have become united to the terrestrial globe. Here interposed the tide, raised by the sun in the plastic materials of the two bodies, and the action of this tide caused the Moon to recede slowly from its primary until it reached its present distance of 238,000 miles. Now the fact that the Earth and the Moon were at this distant epoch almost in contact suggests that they were originally in contact and formed one body. The Moon originally formed part of the Earth, which, in consequence of its very rapid period of rotation, between 3 and 5 hours, and also owing to the interference of the solar tide, split into two, and of these portions the smaller now forms the Moon. The matter which now forms the Moon may have been detached from our Earth as a whole or in parts, but it is almost certain that it was detached from the Earth owing to the rapid rotation of our planet, which made a rupture inevitable. A suggestive speculation due to Professor W. H. Pickering, the well-known American astronomer, is worth mentioning here, so full of interest is it to the Earth's inhabitants. Following up Darwin's work, Professor Pickering considers that, quote, "It will be of interest to determine, if possible, from what part of the Earth the Moon originated. When, says Professor Pickering, the Earth-Moon planet condensed from the original nebula, its denser materials collected at the lower levels, while the lighter ones were distributed with considerable uniformity over its surface. At the present time we find the lighter materials missing from one hemisphere. We find a large mass of material now up in the sky, which is generally believed by astronomers formerly formed part of the Earth, and the density of this material we find to be not far from that of the missing continents. From this we conclude that this mass of material formerly covered that part of the Earth where the continents are lacking, and which is now occupied by the Pacific Ocean." End quote. Professor Pickering also finds a connection between the volcanoes of the Pacific region and the volcanoes of the Moon. This, it is to be remembered, is merely a speculation, with, however, the balance of evidence on its side. It certainly gives a new interest to the study and contemplation of the Moon, when we remember that the silver orb which illuminates our evening skies is formed of materials which once filled the bed of the greatest ocean on the globe. Another interesting fact disclosed by Darwin's studies is that just as the tides raised by our satellite tend to retard the rotation of the Earth, so the tides which the Earth raises in the Moon have the same effect. There is, however, this important difference. There is no water on the Moon. The tides raised by our planet on the Moon did their work ages ago, when our satellite was in a plastic or semi-liquid condition. The superiority of the Earth over the Moon in the matter of size compelled the Moon to rotate on its axis in the same period as it requires to revolve round the Earth. We may now briefly sum up the conclusions to which astronomers have been led. First, we have a globe of molten matter, now known as the Earth, turning on its axis in a very short period. This very rapid rotation, assisted by the tides raised by the sun in both bodies, caused the rupture of the Earth into two bodies, and the smaller now forms the Earth's satellite, which we call the Moon. As a result of continual tidal action, the rotation of the Moon was retarded, and it was forced farther and farther from our planet until it reached its present position. Slowly but surely, the action of the Moon in raising the tides of the ocean is slowing down the rotation of the Earth on its axis, and in the distant future, probably long after the Earth is uninhabitable and dead, our planet will require 55 of its present days to rotate on its axis. What of the time which has elapsed since the Moon was separated from the Earth? This is a matter of some uncertainty, and Professor Darwin's studies place the period of disruption at about 57 millions of years ago. The mind falls back astounded at such a statement, and we can only repeat with deeper reverence the familiar words, quote, 1,000 ages in thy sight are but as yesterday when it is past. End quote. When on a moonlight evening we stand on the seashore and behold the ceaseless ebb and flow of the ocean, with the sound of the waters breaking on the rocks, we have brought to our minds overwhelming thoughts. There is the silver moon, which is constantly operating on our planet, and which, by means of this ceaseless ebb and flow which its action causes, is slowly but surely lengthening our day and slowing down our world. And by a study of the tides we have reached the remarkable conclusion that the same silver moon, our planet's faithful attendant, has been constantly traveling farther and farther from the Earth since that period when it separated from our world, and that period we have calculated as 57 millions of years ago. Truly, of all the wonders of modern astronomy, there are few more astounding than the romance of the tides. End of section 25. Read by Sandra Muskoka, 2022. Chapter 26 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 26. Light and its Mysteries. The foregoing sketch of the universe, from the earth itself to the systems of stars glimmering on the brink of infinity, serves to show that astronomy is, after all, no dry, uninteresting subject, but truly a fascinating and romantic study. Marvelous facts concerning the universe have been brought to light. Suns and planets have been weighed and measured, invisible bodies found by their influence on bright ones, comets traced on their journeys away out into the outer spaces. In short, on all sides, the astronomer has been the victor in the contest with the unknown, although, as Laplace said when he was dying, quote, "What we know is but little, what we do not know is immense." End quote. It is truly remarkable how much knowledge of the universe has been gained by patient observation and careful calculation from observation. How then are we enabled to make observations of the celestial bodies? Our ability is owing to the fact that we see them, that the light rays from these bodies reach our earth and make known their existence to us. Light therefore bears to us the secrets of space. Mention has been made incidentally in previous chapters of many of the characteristics of light and of its velocity, but so far nothing has been said of its real nature. Light emanates from the sun and stars. The light from the sun falls on our world. We're bathed in it, so to speak. Everything on the earth more or less reflects the sunlight. Then it likewise falls on the planets, and like the earth they reflect it back and shine by borrowed sunbeams. The stars all shine by their own inherent light and send it through the depths of space for billions of miles. Light is a vibration sent from the sun, stars, and nebulae across the substance known as ether, which fills all space. But light does not travel instantaneously. It was discovered in 1675 by Rømer, a Danish astronomer, from observing the eclipses of the satellites of Jupiter, that these eclipses are seen later when the Earth is at a greater distance from Jupiter, and earlier when it is at a less distance. He therefore concluded that light requires time to travel. His brilliant idea was confirmed by a succession of illustrious astronomers throughout the centuries, and they all agree that the velocity of light is 186,000 miles per second. Light then does not travel instantaneously. On the Earth, for all practical purposes, it does so. It reaches us from the moon in a second and a half. From the sun it travels in 8 minutes. When we witness, say, a great cataclysm beginning on the sun, we may know that it commenced 8 minutes ago, and that the light has been traveling over the 93 millions of miles which separate us from the sun in the interval. Light then travels at the enormous velocity of 186,000 miles in 1 second of time. It crosses the diameter of the solar system in 8 hours. It takes 4 years to reach us from the nearest of the stars. Sirius, the brightest star of the sky, is at a still greater distance, for light requires 8 years to reach us from that orb. Again, light takes no less than 200 years to reach us from Arcturus, one of the brightest stars in the sky. We can see stars whose light left their surfaces thousands of years ago, stars which, for all we know to the contrary, may be dead and extinct today, but their light has been traveling through space for all these centuries. As an example, we may take the famous new star in Perseus, which was discovered in 1901 by Dr. Anderson. The outburst did not take place in the year 1901, which was merely the year that the light was first seen on the Earth. Astronomers calculated that the outbreak must have taken place about the year 1603 in the reign of King James VI of Scotland. The light from the new star was speeding across the depths of space for 300 years before it reached this Earth of ours. The light which flashed on the Earth from Nova Persei conveyed to the Earth intelligence of a catastrophe which took place 3 centuries ago. This, too, is by no means an extreme case. Light takes several thousand years to reach our Earth from the boundaries of the universe. The various calculations may not be scientifically accurate, but they give us an idea of the vast distances of the fainter star clouds of the galaxy. We do not see the stars as they are. We see them as they were, in some cases centuries ago. Mr. Gore, as mentioned in a previous chapter, has calculated the possible distance of the supposed external universes. Of course, these external universes have never been seen, and we cannot be certain of their existence, but reasoning from probability, astronomers have good grounds for believing in their existence. Mr. Gore's calculation places the nearest of these universes at a distance so vast that light takes 90 millions of years to reach us from its inconceivable distance. The mind is overwhelmed with such an idea. We cannot comprehend 90 millions of years. And yet this is only the nearest of these universes, and if space is infinite, there must be more. There will be an infinite number of such universes scattered throughout an infinite cosmos. Truly, astronomy, at least modern astronomy, is the science of infinity and eternity. What a vast difference there is between the magnificent sweeping conceptions of modern astronomy and the primitive and crude ideas of the ancient astronomers who thought that the Earth was the center of the universe and that the stars were little lamps suspended above the clouds to light up our planet on a dark night. A study of the motion of light and its consequent effect on the heavens leads us to some interesting conclusions. The stars are at different distances, and consequently light takes longer to reach us from some than from others. For instance, light travels from Sirius in 8 years, and from Arcturus in over 200 years. The result of this is that we never see the stellar system as it is at present, or even as it was at any given time. Each of the stars which we see is at a particular distance of its own. One may appear to us as it was 20 years ago, another as it was 1,000 years ago. We see what we may call the ancient light of the stars. Now let us suppose that astronomers were able to construct telescopes large enough not only to enormously magnify the stars, but to show the planets which are revolving around them and the events which are happening on the surface of these planets. Could we observe these planets, we should not see the events which are happening at this moment, but the events of years ago, because light takes time to travel. In the case of a planet revolving round Sirius, we should see not the events of the present time, but the events of 8 years ago. If there are inhabited planets revolving around Sirius, then their light is combined with the blaze of their primary. Could we disentangle the rays and see these planets and their inhabitants, we should behold what was enacted on their surface 8 years ago. We may now invert the idea and apply it to our own Earth, as an American astronomer has expressed it. Quote, "The light from every human action performed under a clear sky is still pursuing its course among the stars." End quote. Suppose that in some of the planets revolving around the stars there exist astronomers who have built telescopes large enough not only to see the planets revolving around the sun, but to see the Earth, its various nations and peoples, and what is going on its surface. At the distance of the nearest star, our sun is reduced to a star of the second magnitude, and all the planets are lost in the solar glare. Still, the idea is correct. The astronomers on planets revolving round Sirius would see the Earth as it was 8 years ago. Similarly, the people on planets moving round the pole star would see the Earth as it was 49 years ago. Likewise, on Arcturus, the Earth would appear as it was 200 years ago. Supposing that from these stars and planets not only the Earth but the countries on its surface, even the little country called Great Britain, could be seen, the inhabitants of some of them would only now be witnessing the Battle of Bannockburn, and others further away would now behold the Battle of Hastings. Still farther away, others would see our country inhabited by wild animals. What does all this teach us? It teaches us that there is no such thing as the past. The events of ancient history, for instance, are past so far as we're concerned, but they are not past in reality. The light from them is still speeding onwards from them through space. As Flammarion expresses it, quote, "The progressive motion of light carries with it through infinity the ancient history of all the suns expressed in an eternal present. Events vanish from the place which brings them forth, but they remain in space." End quote. Of all the romances of astronomy, this is the most romantic. Yet it is all strictly true. It is obvious that we are now treading on half-explored ground, for we have neither the ability nor the instrumental power necessary for us to realize the truth of Flammarion's statement. For instance, we only measure time in days and years, because we live on a little planet revolving round a star. Away out in space, there is no such thing as a period of time, because there is no method of measuring time. And when we cannot measure time, we cannot think of a past. Everything is present. The whole subject is overwhelming and beyond our conception. With our limited understandings, we cannot grasp it in its entirety. In our present existence, we only see these marvels, quote, "through a glass, darkly." End quote. Still, here again we find the oldest of the sciences aiding us in our comprehension of religion, and we at last grasp the meaning of the deep saying of Carlyle, that to God there is neither past nor future, but all is an eternal now. End of section 26. Read by Sandra, Montreal, 2022, as it were. Chapter 27 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 27. How to Know the Stars. Perhaps no one can really appreciate the romance of astronomy without being familiar with the brighter stars and the principal constellations. As Mr. E. W. Maunder puts it, quote, "How great an interest is given to any object by the fact that we know its name. Take some town children out into the country and set them to gather wild flowers. How instantly they ask their names." End quote. It is the same in the case of the stars. When we look at the heavens on a clear night and behold apparently countless points of light, we are lost and overwhelmed with the number of the stars and the complexity of their distribution. One star seems much like another, and we look away from the sky again with neither interest nor curiosity. But if we are told that such and such a star is Aldebaran, and such is Sirius, our interest is aroused, and we naturally desire to trace out the star groups in the heavens and to identify the stars for ourselves. But, asks the would-be astronomer, how is it possible for me to learn the star names and trace the constellations without being taught? Carlyle lamented in his old age, quote, "Why did not somebody teach me the constellations and make me at home in the starry heavens?" End quote. But in reality, no one requires to be taught the constellations. Everyone can best learn them for himself. At the outset, it is true, the task seems impossible of attainment, and some of the hints given in astronomical books only make the task seem more gigantic. When we are told to draw imaginary lines through such and such stars of the plough, and these will lead us to such and such stars in Leo, and will form triangles and quadrilaterals with such and such stars in Cepheus, we feel baffled with the magnitude of the task, and many would-be astronomers fall back in despair and become stargazers, pure and simple. Now, this geometrical method, as we might call it, is all very well after we have acquired a knowledge of the chief constellations. It will then aid us in identifying the various stars of these constellations. But it is open to very serious objections when we're studying the heavens for the first time. Instead of this method, there's another, which, for want of a better term, we may call the pictorial method. The beginner should first possess himself of a revolving planisphere, which shows the heavens at the various seasons of the year, and which is of a convenient size to be taken out of doors. He should then decide which part of the heavens he wishes to consider, and having selected, say, the southern aspect, he should adjust the planisphere to the day and hour and examine it with the aid of a lantern. He will be surprised to find that he can trace without difficulty in the heavens the forms which he sees on the planisphere and the names of which he learns. He sees, for instance, on the planisphere a particular group in the form of a cross, high up and named Cygnus. When he turns his gaze to the heavens, there he can trace this form without difficulty. Where a few minutes ago he could only see an irregular mass of stars, he now sees a star group with a distinct form and its own individuality. Similarly, the observer will pick up other groups in the same manner. No attempt should be made to force the recollection of the groups, but the observer should return night after night to the same part of the heavens. He will be surprised to find that he is beginning to know the constellations without any effort. The configurations are becoming familiar to him, and after a few nights' comparison of the heavens and the planisphere, he will be able to identify Cygnus, Aquila, etc., without the aid of the planisphere. In this manner, the observer may, in the course of a few months, learn all the various constellations. The names, too, of the brightest stars are marked in the planisphere, and he will thus unconsciously learn them also. For instance, he will see that one of the stars in Lyra is very bright. Looking at the planisphere, he will see that it is thereon designated by a special name, Vega, and thus a knowledge of the brighter stars individually is easy. Many are content with a knowledge of the constellations and bright stars, but it is well to be familiar with most of the stars of the second magnitude as well, and also some stars of the fainter magnitudes. For this purpose, of course, the planisphere is of no use. The observer should consult some star maps, or atlas of the stars, but he should be particularly careful in his choice of star maps. By all means, let him avoid those on which are represented what are known as the constellation figures. In such maps we find the plough represented by the figure of a bear, dotted with stars, Cygnus by a star-spangled swan, Orion by a hunter marked with stars. The stars are all inserted and named, but they are lost and confused through the introduction of the constellation figures. These figures are very interesting to the antiquarian and to the astronomer who studies closely the beginning of the science, but they are utterly out of place on such star maps. They existed and exist only in the imaginations of men and have no counterpart in the heavens. Whatever maps the would-be astronomer uses, he should use maps on which only the actual stars are marked. Various excellent maps could be mentioned. In A Handbook and Atlas of Astronomy by Mr. William Peck, astronomer to the city of Edinburgh, there is a good series of charts respecting regions in the heavens which should be of much use to the observer. If the observer, however, wishes to study not regions but individual constellations, he should at once possess himself of Mr. J. E. Gore's excellent guide entitled Star Groups. This latter method of learning the individual stars is really the best. Once the form of the constellation is mastered with the aid of the planisphere, the observer is familiar with the constellation's form and can study each star group individually. At this stage of his knowledge, he will find Mr. Gore's book of the utmost value. The constellations are represented on separate maps, and there are no constellation figures nor even any degrees of measurement. The stars are shown in white on a black background, and with the aid of this book and a lantern, the observer will not only have mastered the constellations, but will have gained sufficient knowledge of the heavens to enable him to begin astronomical observation on his own account. Nothing has been said here of the identification of the planets, and nothing need be said. The student will find no difficulty in recognizing the planets. He will soon learn to recognize the dull yellow glare of Saturn, the soft golden glow of Venus, the steady shining of Jupiter, the ruddy beams of Mars. He may even succeed in catching a glimpse of the elusive wanderer, Mercury, the sparkling one, on some evening or morning when the horizon is clear and the planet well placed for observation. As mentioned in a previous chapter, with the changes of the seasons, new star groups appear, old star groups disappear. In the south we behold the stately procession of the stars nightly across the skies: Leo, Virgo, Gemini in spring, Bootes, Scorpio, Hercules in summer, Cygnus, Aquila, Cetus in autumn, Orion, Taurus, Canis Major, Perseus in winter, while the Plough and the Cassiopeia and the other northern stars surrounding the pole star circle slowly round as the months go by. As the seasons advance, the reappearance of a familiar constellation lends a new charm and interest to the evening walk. As Mr. Maunder has well said, the work of learning the stars has a charm of its own. Quote, "The silent watchers from heaven soon become each a familiar friend, and to any imaginative mind the sense that he's treading the same path as that traversed by the first students of nature will have a strange charm." End quote. Once the observer has learned the constellations, he is able to commence systematic observation on his own account. Even with the unaided eye, he may accomplish work which will at least afford him pleasure if it does not add to the sum of knowledge. With a field glass we may make many interesting observations, while quite a number of celestial spectacles are open to the observer possessing a telescope of 2 inches aperture. In the following list, an account is given of the chief objects of interest in the chief constellations in alphabetical order. Andromeda. The most interesting object in this constellation is the Great Nebula. It may be glimpsed with the unaided eye and is easily seen with the field glass. In a 2-inch telescope it is a very fine spectacle. The chief stars are Alpha, Beta, and Gamma of the 2nd magnitude, and Delta of the 3rd. Aquarius. One of the zodiacal constellations and inconspicuous, its chief stars are Alpha and Beta of the 3rd magnitude, Delta and Zeta between the 3rd and 4th. Aquila, a very striking group, well seen in summer and autumn. The chief stars are Alpha, Altair of the 1st magnitude, and Beta and Gamma of the 3rd. The 3 are on a line. The star Eta is a short period variable with a period of 7 days. It is easily followed with the unaided eye. The galaxy is very brilliant in this constellation. Aries, a small compact constellation. The brightest stars are Alpha and Beta of 2nd and 3rd magnitude respectively. Aries is the first of the zodiacal constellations. Auriga, one of the most notable of the constellations and a good group for binocular observation. The brightest stars are Alpha, the brilliant Capella, of the 1st magnitude, and Beta of the 2nd. Bootes, a straggling constellation which Mr. Maunder believes to resemble the much more striking group of Orion. The brightest star is Arcturus, or Alpha Bootes, of the 1st magnitude. Delta shows in the field glass as a double star. Cancer. This is the smallest and most inconspicuous of all the zodiacal constellations. The only striking feature of the group is the cluster known as Praesepe, or the beehive. It is visible to the unaided eye as a nebulous object, but the least optical aid shows it to be a group of stars. Canes Venatici. This is a very small constellation containing only one conspicuous star, Alpha, known otherwise as Cor Caroli. Canis Major. This group of stars lies too low down to be seen to full advantage in this country. Nevertheless, it is a very fine celestial spectacle. Alpha, or Sirius, is the brightest star in the sky. It forms with Betelgeuse in Orion and Procyon in Canis Minor an equilateral triangle. Although the study and identification of the stars on the principles of lines and triangles is generally speaking to be avoided, this is a figure so regular, so massive that no one can mistake it, and it is useful to remember the names of the three stars which form it. The brilliance of the three and the dearth of brightness within the figure make it a majestic feature of the heavens. The following ancient rhyme, quoted by Admiral Smythe, should assist the beginner to remembering these stars. Quote, "Let Procyon join to Betelgeuse, and pass a line afar to reach the point where Sirius glows, the most conspicuous star. Then will the eye delighted view a figure fine and vast. Its span is equilateral, triangular its cast." End quote. Canis Minor, a very limited group. Its brightest star is Procyon of the first magnitude. Capricornus. This constellation is a good field for the binocular. Alpha of the third magnitude is a visual double star and is well seen with the binocular. It is not a true double star, as the two stars are traveling in different directions and merely appear to be connected because they happen to lie in the same line of vision. Cassiopeia. No one can fail to recognize this constellation, shaped like the letter W, which is on the opposite side of the pole star from the Plough. It is a good binocular field. The region round the star Gamma is a particularly interesting one. The star Alpha is slightly variable in light. Cepheus, a less conspicuous group than the former. Viewed with the binocular, however, there are some fine star fields. A notable triangle is formed by the stars Delta, Zeta, and Epsilon. Of these, Delta is a variable star from the third to the fourth magnitude, with a period of 5 days, 8 hours. In the same constellation is Mu Cephei, the reddest star visible to the unaided eye. It is of the fourth magnitude and was called by Herschel the Garnet Star. It is a striking spectacle in the binocular. Cetus, a long straggling group somewhat difficult to follow. Beta, the brightest, is of the second magnitude. The most notable star in the constellation is Omicron, known as Mira, the wonderful star. It is a notable variable with a period of 331 days. At maximum, its variation may be easily followed by the unaided eye. Corona Borealis. There is not the slightest difficulty in identifying this constellation. Its name, the Northern Crown, suits it exactly, and from its crown shape is easily identified. Its brightest star, Alphecca, of the second magnitude. It is a good field for the binocular. In this constellation appeared the Blaze star of 1866. Corvus and Crater. These are two small, insignificant constellations seen in the south in the springtime. They present little of interest to the beginner. Cygnus. This is one of the finest constellations in the entire heavens. The galaxy is here particularly rich, and fine fields are within the reach of the binocular. Round Alpha there is a remarkable arrangement of the stars, and round Gamma there is one equally striking. Beta is a magnificent double, seen to advantage in a 2-inch telescope. The component stars are yellow and blue. It is interesting to identify the faint stars. One of these, 61 Cygni, is easily visible to the unaided eye. The constellation's most striking feature is the long cross formed by the stars Alpha, Beta, Gamma, Delta, and Epsilon. Of these, Alpha is the brightest and Beta the faintest. Draco, a long, straggling northern constellation. It does not offer many attractions to the beginner. Eridanus, another straggling group seen in the south in winter. Its brightest star is invisible in the northern hemisphere. Gemini. This is a very fine group, easily identified. Its brightest stars are Pollux of the first magnitude and Castor of the second. A little north of Eta is a star cluster just visible to the unaided eye. Zeta is a well-known variable, easily within the reach of the beginner. Hercules. The chief feature of this group is the famous star cluster. It is fairly well seen in a 2-inch telescope. Hydra. Like Draco and Eridanus, this is a straggling group. In the words of Mr. Maunder, it begins close to Procyon under Cancer, and it stretches below the zodiacal constellations of Cancer, Leo, and Virgo, and the greater part of Libra. It has few bright stars, and these grouped in easily remembered figures, and the great reaches of barren sky it includes seem referred to in the name given to its brightest star, Alphard, the solitary. Leo. This is a zodiacal constellation easily identified. Its brightest stars are Regulus of the first magnitude and Denebola of the second. Its most notable feature is the well-known Regulus. In this constellation is the radiant point of the November meteors. Libra, a zodiacal constellation, but very inconspicuous. Lyra, one of the most compact and easily identified groups. Vega is the brightest star and a striking object. Beta is a well-known variable and easily followed by the unaided eye. Ophiuchus and Serpens. These two groups are so intermixed that they may be treated as one. They are among the most difficult of all the constellations in the entire heavens. Serpens presents some good binocular fields. Orion. By common consent, Orion is the most magnificent of all the constellations. Betelgeuse and Rigel are the two chief stars. Rigel is generally the brighter, but Betelgeuse is a variable and at times surpasses Rigel. The red tint of Betelgeuse is very noticeable and contrasts with the bluish-white light of Rigel. The great nebula in Orion is just visible to the unaided eye. A binocular shows it, and it is seen to advantage in a 2-inch telescope, through which it is a striking and awe-inspiring spectacle. Orion has 2 stars of the first magnitude, Alpha and Beta, Betelgeuse and Rigel, and 5 of the second, Gamma, Kappa, Delta, Epsilon, and Zeta, the 3 latter forming the belt of Orion. Pegasus. This is a very notable constellation and a conspicuous feature of the autumn skies. The great square is formed by 4 stars, one of which, however, belongs to the neighboring constellation Andromeda. The square is all the more striking on account of the dearth of stars within. Perseus. To the beginner, Perseus is perhaps the most interesting constellation. The brightest star, Alpha Myrfak, is situated in a magnificent region. Seen with the field glass, there is a curve of stars with Myrfak at the center. Seen with the telescope, the scene is even more striking. Near to the star Chi Persei is a magnificent cluster which can be seen with the binocular and is a magnificent object in a 2-inch telescope. Beta Persei, or Algol, is one of the most remarkable variable stars in the sky. All the variations are within reach of the unaided eye. Pisces. This is a constellation of faint stars, of little interest to the beginner. Piscis Australis. This constellation may just be glimpsed on a clear autumn night when the brightest star, Fomalhaut, of the first magnitude, is to be seen glimmering on the horizon. Sagittarius, a star group deeply immersed in the galaxy, which well repays observation with the binocular. Taurus. This is a constellation of the utmost charm and beauty. In a field glass, its beauties are especially evident. The cluster of the Pleiades is particularly striking in a binocular, as is also the Hyades, the group surrounding Aldebaran, Alpha Tauri, the brilliant red star. Of these 2 clusters, the Pleiades is by far the finest. 6 stars are to be seen by persons of average eyesight, but with a binocular many more are to be counted. Ursa Major. This famous constellation is known to all, at least its chief stars which form the plough. The stars Alpha, Beta, Gamma, Epsilon, Zeta, and Eta are of the 2nd magnitude and Delta of the 4th. Zeta is a double easily seen with the unaided eye. The 2 stars are known as Mizar and Alcor. In a small telescope it is a striking spectacle. Ursa Minor. This group is notable as it contains the pole star of the 2nd magnitude. Virgo, a conspicuous constellation visible in spring. It is shaped like the letter Y. Spica, the brightest star, is of the 1st magnitude. Very little can be done in the study of the planets with the unaided eye or the binocular, but the phases of Venus, the satellites of Jupiter, and the mountains of the Moon are all within reach of a small telescope of 1 or 2 inches in diameter. End of section 27. Read by Sandra, Montreal, 2022.
Chapter 28, Telescopes and Observatories, in the Romance of Modern Astronomy, by Hector Macpherson. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy, by Hector Macpherson. Chapter 28, Telescopes and Observatories. The greater part of our knowledge of the science of astronomy is due to the marvelous instrument known as the telescope, which by magnifying the celestial bodies enables men to study them at much less than their actual distance. Before the invention of the telescope, there was certainly a science of astronomy, but it was chiefly a science of statistics, star catalogs, star positions, planetary positions, and apparent motions. Nothing was known of the surface of the moon, although it lies so close to us. Without the telescope, mankind would have remained in comparative ignorance of the outer universe. It is wonderful, then, that John Kepler addressed the newly invented instrument in these words: "O telescope, instrument of much knowledge, more precious than any scepter, is it not he who holds thee in his hand made king and lord of the works of God?" Telescopes are of two kinds: the refracting telescope, the most familiar, and the reflecting telescope. Of these, the refractor was the first to be invented. The first telescope was constructed in 1609 at Middelburg in Holland by an optician named Lippershey. The news of the construction of the first telescope reached Italy in the summer of 1609, when the idea of constructing one presented itself to the fertile mind of Galileo. In a letter dated August 1609, Galileo wrote, "About 2 months ago, a report was spread here in Padua that in Flanders a spyglass had been presented to Prince Maurice, so ingeniously constructed that it made most distant objects appear quite near, so that a man could be seen quite plainly at a distance of 2 miles. This result seemed to me so extraordinary that it set me to thinking, and as it appeared to me that it depended upon the laws of perspective, I reflected on the matter of constructing it, and was at length so entirely successful that I made a spyglass which far surpasses the report of the Flanders one. The effect of my instrument is such that it made objects 50 miles off appear as large as if there was only 5. Such were the humble beginnings of the telescope, the instrument which revolutionized the science of astronomy. Galileo constructed a number of telescopes. The first was of little scientific value. The second was more useful, and with the third he commenced his observations on the moon. With his fifth instrument, he discovered the satellites of Jupiter. The principle of the Galilean telescope is very simple. It is the simplest form of refractor through which the observer looks directly at the object of observation. The object glass, or large glass at the end, was, in the Galilean telescope, a simple convex lens. After Galileo's time, larger telescopes were constructed, but they were practically worthless owing to a difficulty of construction which for a time seemed insurmountable. Owing to the dispersion of light, the principles of which cannot be explained in a work like the present, the image of the object was not well shown, the edges having fringes around them similar to the colors of the rainbow. This phenomenon, known as chromatic aberration, increased as the object glasses increased in size. For some time, indeed, astronomers endeavored to surmount the difficulty by making telescopes immensely long. Huygens, Bianchini, and Cassini, astronomers of the 17th century, constructed telescopes over 100 feet in length. They were very unwieldy, and little scientific work of importance was accomplished by means of them. Accordingly, Sir Isaac Newton, who devoted much attention to the subject, came to the conclusion that it was impossible to construct a refracting telescope which would be free of this defect. The same view was reached about the same time by the Scottish astronomer James Gregory. Both Newton and Gregory agreed in condemning the refractor, and both commenced to devise a new form of telescope. The form of telescope devised by them was the reflector, an instrument formed on the principle of reflection of light. In this form of telescope, the light coming into the telescope from the object to be observed was reflected into the eyepiece from the surface of a concave mirror constructed of alloy known as speculum metal. Gregory and Newton constructed instruments which, while similar in principle, differed slightly in detail. One of the drawbacks of the reflector is that a second reflection is necessary before the rays from the object under observation can enter the eyepiece. If the observer looked down the tube of the telescope at the image, he would at once cut off the light from the object he wished to observe. Newton, therefore, in his telescope, placed the eyepiece in the side, and into it the rays were deflected by a second reflection. Gregory, on the other hand, put the eyepiece immediately behind the principal mirror. The Newtonian form is the one most used. After Newton's invention, the reflecting telescope became very popular. Its chief development was due to Sir William Herschel, who gave it immense popularity. It is a remarkable illustration of the sequence of events that Herschel's development of the reflecting telescope was due to the fact that he was at first an amateur astronomer who obliged to make his own telescope. He constructed many reflectors and devised a modification of the Newtonian form, known as a Herschelian. In 1775, Herschel constructed his 7-foot telescope, and, after making instruments of 10, 20, and 30 feet in focal length, he constructed in 1789 the famous 40-foot reflector with which he discovered the inner satellites of Saturn. In the hands of Herschel, the reflecting telescope seemed to exhaust its possibilities, and men began to turn their attention to the despised refractor. In the 18th century, it was found to be possible by combining lenses of flint and crown glass in the object glasses of refractors to practically eliminate the aberration which had put a check on the advance of the refracting telescope. For some time, it was found difficult to procure object glasses of flint glass of sufficient size to make any considerable advance in telescope construction. However, in the hands of a firm of Swiss opticians, remarkable progress was made, and in 1823, a lens of 12-inch diameter was successfully finished. Meanwhile, the greatest development of the reflecting telescope was soon reached. Most people have heard of Lord Rosse's telescope. It is, in point of size, about the largest telescope in the world, although its situation in the unfavorable climate of Ireland has rendered it practically useless within recent years. The history of this telescope is so interesting that it is worth giving it at some length. When quite a young man, the 3rd Earl of Ross conceived the idea of erecting the largest telescope in the world on his estate in Ireland. Being an amateur, he turned his attention to the reflecting telescope. As the late Miss Clark pointed out, he had to rely entirely on his own invention and to earn his own experience. He had no skilled workmen to assist him. His implements, both animate and inanimate, had to be formed by himself. Peasants taken from the plow were educated by him into efficient mechanics and engineers. In 1827, he began to work, and it was not until April 1842, 15 years later, that he succeeded in constructing the famous mirror, 6 feet in diameter, with which he was to survey the heavens. By February 1845, the telescope was ready for work. A tube, which resembled when erect one of the ancient round towers of Ireland, served as the habitation of the great mirror. The tube was no less than 58 feet long and 7 feet in diameter, so that when it was horizontal, a man of considerable height could walk through it holding an umbrella. Sir Robert Ball, for whom some years had charge of the great telescope, has the following interesting description of the instrument. Almost the first point which would strike the visitor to Lord Rosse's telescope is that the instrument at which he is looking is not only enormously greater than anything of the kind he has ever seen before, but also that it is something of totally different nature. In an ordinary telescope, he is accustomed to find a tube with the lenses of glass at either end, while the large telescopes that we see in our observatories are also in general constructed on the same principle. At one end there is an object glass, and at the other end the eyepiece. And of course it is obvious that with an instrument of this construction, it is to the lower end of the tube that the eye of the observer must be placed when the telescope is pointed through the skies. But in Lord Rosse's telescope, you would look in vain for one of these glasses, and it is not at the lower end of the instrument that you are to take your station when you are going to make your observations. The astronomer at Parsonstown has rather to avail himself of the ingenious system of staircases and galleries by which he is enabled to obtain access to the mouth of the great tube. Many valuable observations and discoveries were made by means of the Rosse telescope during the first few years of its existence. but it was not long before the powers began to deteriorate. Its situation in the unfavorable climate of Ireland greatly injured its usefulness, and it is now a little more than an astronomical curiosity. It had only a few brilliant years of investigation and discovery. About the time the Ross telescope was erected, a new material for the construction of reflecting telescopes was invented by two independent French investigators: glass upon which a thin film of silver is deposited. These instruments have a light-gathering power far exceeding the telescopes whose mirrors are constructed of speculum metal. In June 1847, there was erected the famous Harvard refracting telescope of 15-inch aperture. This was the beginning of the development of the refractor. A 23-inch telescope on the same lines was conducted by a self-taught English optician in 1868, while a year or two later, another self-taught optician in America followed with the construction of the famous 26-inch telescope of the Washington Observatory, rendered famous by the discovery by the late Professor Hall, while using it, of the satellites of Mars. Next in the 80s came the erection of telescopes of 29.5 inches and 30-inch aperture, respectively, for the observatories of Nice in France and Pulkowa in Russia. The 30-inch telescope of the Russian National Observatory was for some years the greatest refracting telescope in the world. But it did not retain this position for long. As one writer put it, the Tsar of all the Russias was outbid twice by an American millionaire. The first of these was James Lick, whose name is now immortalized in connection with the great observatory in California, where so many discoveries have been made. The story goes that Mr. Lick, a California millionaire, being very desirous of erecting a permanent memorial of himself and his wife, proposed to leave money for the erection of two immense statues on the Pacific coast. About this time, however, an astronomer suggested that in case of war, such statues would be liable to destruction by the enemy, and that a great telescope erected on one of the mountains in California would be much safer. Accordingly, Lick took up with much enthusiasm the erection of a gigantic telescope, making it a condition, however, that his remains would be interred below the base of the instrument. He died many years before the observatory was completed. The late Professor Newcomb remarks that the erection of an observatory was not in the millionaire's mind. All he wanted was a gigantic telescope. From his point of view, as indeed from the point of view of the public generally, the questions of telescopic vision is merely one of magnifying power. An observatory was, however, necessary in order to afford a house for the great telescope, but the idea of having the most powerful refracting telescope in the world was kept in view, and at last an object glass 36 inches in diameter was constructed. The observatory was placed on Mount Hamilton, a lonely elevation 4,250 feet high in California, amid the purest air where the largest instrument could be used to an advantage. In 1888, the observatory was finished, and the great Lick telescope entered a long career of usefulness. Unlike the magnificent telescope of Lord Rosse, ruined by its situation in a poor climate, the great Lick telescope is still in the prime of its life. The discovery of new double stars, of a new satellite of Jupiter, the measurements of nebular motion, within a few years of the erection of the telescope, is a testimony not only to the excellence of the instruments, but still to the skill of the observers. Men such as Professors Burnham, Barnard, Keeler, and Campbell, whose names are deservedly famous in astronomy. The colony of astronomers on Mount Hamilton is isolated from the rest of the world, and it requires a considerable amount of self-sacrifice to pursue astronomy under those conditions. To those in actual charge of the telescope, says a well-known astronomer, the situation is not without its disadvantages. They are at some distance from the town and without many of the comforts of civilization. The winter on the mountain is severe, and brings with it at times considerable privations. In one winter, there was actually no water to drink except what had passed through the engines. The great Lick telescope enjoyed for about 10 years the place of the greatest telescope in the world. At length, Mr. Yerkes, another millionaire, gave to the University of Chicago money to equip an observatory and erect a telescope 40 inches in aperture, 4 inches greater than the Lick telescope. This great telescope was set up in 1898 at the new observatory of the University of Chicago, Williams Bay, Wisconsin, 80 miles from Chicago. Here it is in the hands of expert observers. Foremost among the other astronomical institutions in America must be placed the Carnegie Observatory on Mount Wilson in California. Dr. Andrew Carnegie, unlike Messrs. Lick and Yerkes, is deeply interested in all things scientific, and his donations to the Carnegie Institute have conferred inestimable benefits on astronomy and astronomers. In 1905, the Carnegie Observatory on Mount Wilson was founded, and its head was placed Professor Hale, one of the most distinguished astronomers of the United States. Among the instruments erected here are the 60-inch reflector, with which much important work has been done, while greater things are expected from the 100-inch silver-on-glass reflector, which surpasses Lord Rosse's famous telescope in the point of size. Like the Lick Observatory, the Carnegie Observatory is isolated from civilization, and it is a matter of self-sacrifice to be an astronomer on Mount Wilson. The view that a certain atmosphere is essential to good astronomical work has been maintained for many years by Professor Percival Lowell, who established in 1894 the now famous Lowell Observatory in Flagstaff, Arizona. Here he erected his 18-inch and 24-inch refractors, which he claims to be almost unrivaled for space-penetrating power, and here he also proposes to erect a 40-inch reflector for photographic purposes. Work amid surroundings so far removed from human habitation entails, as we have remarked, a good deal of self-sacrifice. But, as indicated by Professor Lowell's remarks, it seems to have also a certain charm. To sally forth into the untrod wilderness in the cold and dark of a winter's small hours of the morning, with the snow deep upon the ground and the frosty stars for mute companionship, is almost to forget oneself a man for the solemn awe of one's surroundings. Fitting portal to communion with another world, it is through such avenue one enters on his quest, where the common and familiar no longer jostle the unknown and strange. The Harvard College Observatory in Massachusetts has none of the advantages of the great institutions already named, so far as climate is concerned, yet it has a reputation and a record second to none. Professor E.C. Pickering, the director of the observatory, has raised the institution to a high standard of efficiency. Photographic work is one of the specialties at the observatory. He charts the sky once a month with a smaller instrument, and on a smaller scale. He charts the brighter stars every fine night, so that if a star brighter than 6th magnitude makes its appearance in any part of the heavens, he would have a record of it on the first clear evening. Turning from the great institutions of the New World to the more historically interesting observatories of the Old, we find two, Greenwich Observatory and Paris Observatory, which have the greatest historical interest in the world. The Paris Observatory was erected a few years before the sister institution, being completed in 1671. 4 years later was laid the foundation stone of the Royal Observatory of Greenwich, of which the famous John Flamsteed was made director with the title of Astronomer Royal. It is not too much to say that the science of practical astronomy was founded at Greenwich. The work of Bradley, the third Astronomer Royal, forms an epoch in the history of astronomy. The history of this great and honorable institution would take too long to record here. The object for which the observatory was founded, practical astronomy, is still regarded as the chief side of the work, and for this a large instrument is not required. Still, Greenwich is at the same time thoroughly progressive, and a good deal of photographic and observational work is done. The observatory boasts a 28-inch refractor, a very fine instrument. The Paris Observatory is also deservedly famous, having been presided over by a succession of famous men who have done much for the development of astronomy. These two observatories occupy the chief places among the institutions in Europe for the cultivation of astronomy. Other famous observatories in Europe include Edinburgh, Potsdam, Pulkowa, Heidelberg, Milan, and Rome. The Edinburgh Observatory was founded in 1776, a century after the Greenwich Observatory, and was originally the property of the Astronomical Institution of Edinburgh, being erected for the convenience of members of the institution who wished to make practical observations. It was enlarged in 1811, and with its instruments, the famous astronomer Henderson, who first measured the distances of the stars, made his earliest observations. In 1834, the observatory, which occupied a fine position on Carlton Hill, Edinburgh, became government property. It was converted into a royal observatory, and at its head was placed Thomas Henderson, Professor of Astronomy at the University of Edinburgh, who became Astronomer Royal of Scotland. In 1896, a new Royal Observatory was erected on Blackford Hill in the outskirts of the city, away from the smoke of the city. The new institution is second only to Greenwich among British observatories. The old observatory buildings on the Carlton Hill were acquired by Edinburgh Town Council. The council converted them into a city observatory mainly for educational purposes. It, however, possesses the largest telescope in Scotland, a 22-inch refractor. The observatory at Potsdam is equipped with a magnificent 28-inch refractor. This institution is known as the Astrophysical Observatory because the new side of astronomy, the study of astrophysics, the physical investigation of heavenly bodies, is chiefly pursued there. The observatory was founded in 1874 and was the scene of the labors of the great German astronomer Vogel. Pulkowa Observatory was founded in 1835 by the Tsar of Russia. It was equipped with what was then one of the greatest telescopes in the world, while one of the most famous astronomers, William Struve, a German observer, was placed at its head. In 1884, under his son and successor, Otto Struve, the observatory was furnished with what was, at the time, the greatest telescope in the world. It is now, however, much behind the American observatories in point of size of its telescopes. It has been directed by a succession of very able astronomers. The Heidelberg Observatory is one of no great antiquity, but its record is a noble one. It was erected in 1893, and at its head was placed Professor Max Wolf, the great astronomical photographer. Here was erected the famous photographic telescope by means of which Dr. Wolf has secured his beautiful photographs. The Italian observatories of Milan and Rome are famous chiefly from the historical interest which attaches to them. The Bera Observatory in Milan was the scene of the work of Professor Schiaparelli for upwards of 40 years. Favored with a magnificent sky and a fair-sized instrument, Schiaparelli certainly made the most of his opportunities. The Observatory of Rome was the scene of the labors of two distinguished men, Secchi and Ticini, who favored the beautiful climate of Italy, were also enabled to make the most of their opportunities in a different field of astronomical research, solar and stellar physics. Among the observatories in the southern hemisphere, 3 may be mentioned specifically. The Cape Observatory, the scene of the work of Thomas Henderson and more recently of Sir David Gill, the Cordova Observatory in Argentina, and the Observatory at Arequipa in Peru. The last named is the Southern Observatory Station of Harvard College Observatory, which thus surveys both hemispheres of the sky. End of Chapter 28.
Chapter 29 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Kathy Kay. The Romance of Modern Astronomy by Hector Macpherson. Chapter 29. The Romance of Discovery, the Early Astronomers. In the previous chapters, reference has been made to the vast amount of knowledge which has been amassed by the human race concerning the universe and the place of our world in nature. In the early ages of our world's history, mankind was sunk in ignorance regarding the heavenly bodies, as was clearly shown in the opening chapter. Today we have acquired a considerable insight into the system of the universe at the present time, and have even dared to attempt to read the past of the universe and to trace its future. The advance of astronomy throughout the ages has been like that of a mighty army marching to victory. The march has been a triumphal progress so far, but we are no nearer the end, for as soon as one stage of the journey is reached, new and unfathomable vistas come into view. Carlyle has remarked that the history of the world is the history of its great men, and it is equally true to say that the history of astronomy is the life story of the astronomers. Of these, the earliest are lost in the mists of antiquity, and the name of the first astronomer will probably remain forever unknown. In the early ages, students of the heavens were not merely astronomers. Thus, Aristotle, who exercised so profound an influence on astronomy, was an all-round scientist and philosopher. The first astronomer in the actual sense of the word was Hipparchus. He was born about 170 B.C. He constructed a catalogue of the positions of the stars, an idea supposed to have been suggested by the appearance of a temporary star. Hipparchus died about 120 B.C. Over 200 years later, Ptolemy described him as a most truth-loving and labor-loving man. One of the most famous of the ancient astronomers was the Egyptian Claudius Ptolemy, who is supposed to have lived at Alexandria between about AD 127 and 157. Ptolemy's ideas of the universe were believed for 1,400 years, and he propounded the famous Ptolemaic theory, which was eventually upset by Copernicus. Ptolemy considered, like Aristotle, that the earth was round and immovable. The celestial bodies were thought to revolve around it in the following order: the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and the stars proper. The planets were believed to revolve in circles round imaginary centers, which revolved in circles round the earth. This theory was preserved in Ptolemy's great work, the Almagest. After the death of Ptolemy, the science of astronomy was taken up by the Arabians, the chief of these being Ulugh Beg, king of Samarkand, who lived in the 15th century. He made a catalogue of the stars more perfect than that of Hipparchus, and it remained the finest until the days of Tycho Brahe. Ulugh Beg was assassinated by his son, who desired the throne, in 1447, 26 years before Copernicus was born. It had become plain even before the time of Ulugh Beg that the theory of Ptolemy was very complicated. Eventually, Alfonso X, king of Castile, who took a great interest in astronomy, on hearing explained to him the Ptolemaic theory, declared that if he had been consulted at the creation, he could have given some useful hints. This is often considered to have been an irreligious remark, but we must remember that Alfonso X was dissatisfied with Ptolemy's views. The ancient astronomers ended up with Ulugh Beg. Though Pythagoras had said that the earth moved, the end of the 15th century found the world more ignorant of astronomy than it had been in the time of Aristotle and Hipparchus. Astronomy was therefore prepared for the revolution of Copernicus. The system of astronomy according to Aristotle and Ptolemy was implicitly accepted during the Middle Ages. The Church of Rome contrived to make the Ptolemaic system agree with its own particular interpretation of the Bible, and thus it was that nobody thought of questioning whether Aristotle was right or wrong until Copernicus came upon the scene. As has been well said, all who in these days value freedom of thought, every man who now follows freely and honestly the leading of the mind and conscience God has given him, owes no small debt to the old monk who in the solitude of the monastery garden at Frauenburg thought out the overthrow of the authority of Aristotle. Nicholas Copernicus, the founder of modern astronomy, was born at Thorn, on the Vistula in Poland in 1473. He was the son of a tradesman named Nicholas Copernicus, and his uncle was the bishop in the cathedral of Frauenburg. It has been pointed out as a remarkable coincidence that the great astronomer had just reached manhood when Columbus discovered America. Copernicus was educated at the University of Krakow, where he devoted himself first to medicine and philosophy, and afterwards to astronomy, mathematics, and painting. After spending some years in various parts of Italy, Copernicus in 1500 went to Rome and was appointed professor of mathematics. Here he studied astronomy in earnest and was universally acknowledged to be a great man of science. He did not remain long in Rome, but returned to Poland, where he settled at the Cathedral of Frauenburg as a priest, devoting himself to astronomy and to his duties as an ecclesiastic. He was of a grave and serious nature, and made only a few intimate friendships. Early in his career, Copernicus came to doubt the truth of the Ptolemaic theory on account of its complications. He noticed that everything was done in nature by the simplest methods. Every new irregularity which was discovered in the motions of the planets required a new epicycle, making the system of Ptolemy so complicated that it could scarcely be understood. Another great difficulty which Copernicus noticed was that the stars were represented as revolving round the earth in the short space of 24 hours. Some suggestions that had been made by the ancient Greeks specially struck him. Nicetas had suggested the rotation of the earth on its axis to account for the diurnal motion of the heavens, a suggestion which Ptolemy considered and rejected. Philolaus thought that the earth moved and not the sun. These considerations led Copernicus to revolutionize men's ideas of the entire planetary system. The first great discovery of Copernicus was that of the rotation of the Earth on its axis, an argument which Ptolemy had used in trying to prove that the Earth did not rotate, namely that there would be such a rush in the atmosphere as would carry men off the surface. Copernicus answered by showing that the inhabitants would be carried by the Earth in the same manner as a man carries his overcoat. Copernicus also showed that it was much simpler for the Earth, along with the other planets, to revolve round the Sun, in an orbit between those of Venus and Mars, than for the Sun and planets to revolve round the Earth. He also said that, if his opinions were correct, Venus and Mercury should exhibit phases like the Moon. In the case of Venus, these phases were discovered telescopically by Galileo in 1611, and Mercury was also proved afterwards to show phases. In the case of the stars, Copernicus made little advance. The absence of parallax on account of the Earth's motion was for long considered a great drawback to the Copernican theory. Copernicus declared that the distance of the stars must be so enormous that there would be little or no parallax. Copernicus did not at once publish his great discoveries. Still, his opinions were well known. Men of science flocked to Frauenburg out of curiosity to know of the new system, and went away convinced that it was true. Copernicus's friends had repeatedly urged him to have his works published in book form, but he refused. An event happened, however, which caused him to give his system to the world. A young admirer, George Joachim, or Rheticus, gave up his position as professor of mathematics in the University of Wittenberg in Germany in order to go to Frauenburg to hear the opinions of Copernicus. He soon became convinced of the truth of the Copernican system. In 1541, when Copernicus was an old man of 68, he agreed to give his book to the world, and gave over the care of the publication to Rheticus, who had the book printed at Nuremberg in Germany by a man named Andrew Osiander. The great work, which is entitled De Revolutionibus Orbium Celestium, was published in 1543. Osiander, who published it, was afraid of the opposition which it would arouse, and wrote a preface to the book, saying that the opinions of Copernicus were merely founded on theory, and need not be received as true. Copernicus died suddenly at the age of 70 on May 23, 1543. A few hours before his death, he received the first copy of his great work. He was buried in the Cathedral of Frauenburg, and no mention of his great discoveries was made on his tombstone. Not until 30 years after his death was any memorial erected to his memory. When he died, astronomy was left in a most unsettled state. The tables of the planetary motions predicting eclipses, conjunctions, oppositions, being based on the observations of the Greeks and the Arabs, were often several hours or days wrong. It was thus obvious that until the motions of the planets had been more correctly investigated, the question of the true system of the world must remain more or less unsolved. 3 years after the death of Copernicus in 1546, there was born at Knudstrup in Denmark one who was destined to place astronomy on an entirely new basis, that of exact observation. His name was Tycho Brahe. He was the eldest son of a Danish nobleman, Otto Brahe, and was educated by his uncle, George Brahe. When he was 13 years of age, he was sent to the University of Copenhagen, and an eclipse of the sun which happened in 1560 directed his thoughts to astronomy. His uncle, however, desired him to study law, and to take his attention from science, sent Tycho to the University of Leipzig in Germany. Dr. Dreyer, to whom all interested in astronomy are indebted for his admirable biography of the great Danish astronomer, informs us that Tycho was accompanied to Leipzig by a young man named Vedel, who acted as his tutor. George Brahe had instructed Vedel not to allow Tycho to continue studying astronomy, which in those days was looked upon as a waste of time, and a most undignified occupation for the son of a nobleman. But Tycho was not to be diverted from science, having no interest whatsoever in the study of law. He bought, unknown to his tutor, a small celestial globe in order to know how to find the stars. He could only use it while Vedel was asleep. Tycho's first instruments were a pair of compasses, one leg of which he could point at the object observed, and the other at some known fixed star, and so could measure their angular distance apart. By this time Vidal had found that Tycho had no interest in law. Tycho's uncle died in 1565, and he was free to study the stars. His relatives, who considered it a disgrace to study astronomy, began to despise him, but nothing would now distract him from his favorite study. Being looked upon with contempt by his relations, Tycho in 1566 left Denmark for Germany, settling at Wittenberg in April and at Rostock in September. At Rostock, 2 events took place of great interest. In the earlier part of his life, Tycho was a firm believer in astrology, and he declared that the eclipse of 1566 foretold the death of the Sultan of Turkey. Some time later the news arrived that the Sultan was dead, but that he had died before the eclipse. It is satisfactory to know that Tycho gave up his belief in astrology at a later period of his career. He had a violent temper, and in the end of 1566 quarreled with another Dane living at Rostock as to which was the better mathematician, the result being that a duel was fought in which Tycho was seriously wounded. Tycho Brahe had come to the conclusion that the true arrangement of the planetary system could not be ascertained until the planets and stars had been carefully observed and their positions noted, instead of relying on the primitive and imperfect observations of the Greeks and Arabs. After leaving Rostock, he went to Augsburg and erected in that town for the brother of the burgomaster a large quadrant for noting the positions of the stars. In those days the telescope was unknown, and quadrants and sextants were the principal instruments of astronomers. In 1570 Tycho left Augsburg for Denmark. About this time Tycho's time seems to have been occupied with chemistry, and one of his uncles permitted him to use an outhouse as a laboratory. Tycho pursued the study of chemistry until 1572, when a great astronomical event finally directed his attention to the stars. On November 11, 1572, when Tycho was returning from his laboratory, he observed a brilliant new star in the constellation Cassiopeia. At first it rivaled Venus in brilliancy, and Tycho's observations showed that it had no parallax, and was therefore among the stars, and did not belong to the planetary system. The light of the star now rapidly faded, but Tycho made many important observations on it. He published a book on the star named De Nova Stella, in which he gave a detailed description of all the observations which he had made. The publication of this work greatly annoyed Tycho Brahe's proud relations, who considered it undignified for a nobleman to write a book. In 1574 Tycho lectured on the stars in Copenhagen, but he had already made up his mind to leave Denmark and settle in Germany. King Frederick II of Denmark saw that honor would be conferred upon his country if he could persuade Tycho to remain in Denmark. In 1576, therefore, the king granted to Tycho a pension and the use of the island of Ven near Copenhagen, on which he might build an observatory to carry on his studies. Tycho accepted the offer, and the observatory was entirely completed by 1580. It was called Uraniaborg, or the City of the Heavens, and it was there that Tycho accomplished that work which has given him a place among the greatest astronomers who ever lived. He made observations on the planets of the utmost importance, and he formed a star catalogue. When Tycho went to observe the stars, he put on robes of state, as it was his belief that he could not show enough reverence when entering the presence of the great orbs of heaven. In 1577, Tycho dealt a severe blow at the authority of Aristotle by upsetting the ancient views of comets. Aristotle had declared that comets were atmospheric and much nearer than the moon, but Tycho showed that they were situated among the planets. In 1588 he published a book on the comet of 1577, and in this he gave to the world the Tychonic system. Tycho Brahe was opposed to the view of Copernicus, though he had a high opinion of the great astronomer. He likewise opposed the Ptolemaic system, and was led to found the Tychonic system, a combination of the Ptolemaic and Copernican theories, in which the planets were believed to revolve round the sun, which along with the moon and stars revolved round the earth. This error was, however, of little importance, as it was in observational astronomy that the great work of Tycho was accomplished. Tycho remained at Ven for 20 years. In 1588, King Frederick died and was succeeded by his son, King Christian IV, then only 11 years of age. In 1597, he took the power into his own hands, and several serious charges were brought against Tycho. He had been given a cathedral which he had allowed to fall into disrepair. He had quarreled with one of the people of Vien, and the high noblemen were jealous of his pension. Tycho had a quick temper, but this does not at all justify King Christian in stopping Tycho's pension and forbidding him to carry on his observations at Copenhagen. In June 1597, Tycho and his family left Denmark forever and settled in Germany. The great astronomer moved restlessly from place to place. He wrote from Rostock a humble and kindly letter to the king, asking him to restore his pension. But Christian refused, and after 2 years of wandering over Germany, Tycho settled at Prague in Bohemia in 1599. He was honored by the Emperor Rudolf of Bohemia by his appointment as imperial mathematician, and in 1600 Kepler became his assistant. But though only 54 years old, the anxiety and exile from Denmark proved too much for Tycho, and after a short illness he died at Prague on October 24, 1601. For some time before his death he was heard to exclaim, "Ne frustra vexisse videre. Oh, that I may not be found to have lived in vain." He asked Kepler to use the observations made by him and to publish them as the Rudolphine Tables. Tycho was buried in Prague, where a great statue was erected to his memory. Had it not been for Tycho, the truth of the Copernican theory, which he opposed, would not have been proved for many years after. To Tycho Brahe we owe the foundation of accurate observation, which has made astronomy the most exact, the most wonderful of all the sciences. End of chapter 29. Chapter 30 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Kathy Kay. The Romance of Modern Astronomy by Hector Macpherson. Chapter 30. The Romance of Discovery, Galileo and Kepler. While Tycho Brahe rejected the Copernican system in favor of an idea of his own, there were living two men who spread the new theory in Italy and Germany. These men were Giordano Bruno and Michael Maitland. Bruno spread the new theory in Italy and also in England in a more daring manner than Maitland did in Germany, and for refusing to abjure his belief he was burned alive as a heretic at Rome in 1600. Maitland was the tutor of Kepler and informed him of the truth of the system of Copernicus. As yet, however, nobody had proved the truth of the theory, and when it had been rejected by such a great man as Tycho Brahe, it seemed as if it must still remain a theory. It was here that there came into fame the great Italian astronomer who proved that the Copernican theory was true, and who suffered the most cruel persecution at the hands of the Church of Rome. Galileo de Galilei was born at Pisa in 1564. He was the eldest son of Vincenzo de Bonhuti de Galilei, an Italian nobleman residing at Pisa. At first his father intended him to be a cloth merchant. He was sent to a school in Vallombrosa and made such progress in his studies that his father decided he should adopt the profession of medicine. When he was 17 years of age, Galileo entered the University of Pisa. In a short time he learned mathematics, which he studied with great perseverance, much to the displeasure of his father. Galileo had not been long at the university when he perceived that Aristotle was by no means an infallible guide in scientific affairs, and he was not afraid to ridicule the Aristotelian authority, much to the annoyance of the professor at Pisa. He also devoted himself to painting and music, and for some time intended to become an artist. When he was 21 years of age, Galileo left the university, and 4 years later he was appointed professor of mathematics at Pisa. Here he made his first great attack on the Aristotelians. Aristotle had declared that if two bodies were dropped to the ground from the same height, the heavier would reach the ground before the lighter. Galileo said that both would reach the ground simultaneously. To prove that he was correct, Galileo, in presence of a large number of people, dropped two bodies of unequal weight from the top of the Leaning Tower of Pisa. Both reached the ground at the same time. This was a triumph for Galileo, but instead of admitting that they had been wrong, the Aristotelians made his professorship at Pisa so unpleasant that he resigned. In 1592 he was appointed professor of mathematics at Padua. Here he lectured on scientific subjects with great popular success. In 1602 he invented the thermometer. In a letter to Kepler in 1597, Galileo remarked that he had adopted the Copernican system many years before. At first he had laughed at the new idea, but he found that while many of the followers of Ptolemy had become Copernicans, no follower of Copernicus had ever adopted the old system. Galileo, however, was forced to teach the Ptolemaic system at the university, keeping his views to himself. But the greatest of Galileo's discoveries had yet to come. Hearing that Lippershey, a Dutch optician of Middelburg, had made an instrument by which a man at a distance of 2 miles could be clearly seen, Galileo at once set about constructing an optic tube, as a telescope was then called, and when he had made one there was quite a rush to see it. In 1609 he presented a little tube to the Senate at Venice. He then made another and more powerful telescope, the style of which is now known as the Galilean refractor. He was amazed to find that he could see 10 times as many stars through the telescope as he could see with the naked eye. He examined the Pleiades, Orion, the cluster Praesepe, and other star clusters. The Milky Way was now resolved into stars. In January 1610, Galileo directed his telescope to Jupiter. He noted 3 stars near the planet. Next night, to his amazement, he found that the 3 stars had moved, as well as Jupiter. Some nights later a 4th was discovered, and Galileo concluded from their changing positions that they revolved round Jupiter, as the moon revolves around the earth. Some nights later a 4th was discovered, and Galileo concluded from their changing positions that they revolved round Jupiter, as the moon revolves round the earth, and the planets round the sun. This confirmed the truth of the Copernican theory. Several people, as already mentioned in a previous chapter, refused to look into the telescope in case they might see the satellites and be convinced. Galileo discovered some time later that Venus exhibits phases similar to the moon. Copernicus had said that Venus would show phases if his theory was correct. Once again, Galileo confirmed the truth of the Copernican system. He also examined the moon and discovered that its surface was covered with mountains and craters. He found that the sun had black spots on its surface, that Mars showed phases, greatly to the disgust of the Aristotelians. Galileo next discovered that the planet Saturn was elliptical in shape, but he could not explain the cause. It was not explained until Huygens took up the subject in 1656. Galileo left Padua in 1610 and went to Florence with the title of mathematician and philosopher to the Grand Duke of Tuscany. In leaving Padua he made a great blunder in transferring himself from the Free Republic of Venice to Tuscany, where the Church of Rome was all-powerful. At length Galileo's ideas about the universe, now widely known, were pronounced to be opposed to the Bible. In 1615 he went to Rome and continued to teach the Copernican theory. For this he was summoned before the Inquisition, and the Copernican system was condemned. Pope Paul V warned Galileo not to teach the new system as if it were true. After Paul V was dead, in 1623, Cardinal Barberini was elected pope as Urban VIII. The pope had been, while still a cardinal, a great friend and admirer of Galileo, and the astronomer therefore considered that he was now at liberty to teach the Copernican theory. He prepared to write his work, The Dialogue of the Two Principal Systems of the World, the Ptolemaic and Copernican. It was written in the form of conversations between 3 men. Galileo was very careful, and by writing it in the form of conversation, which did not indicate the views of the author, he obtained permission from the Pope and the Inquisition to have his work published. The book was given to the world in June 1632. Presently, however, the Church of Rome regretted having allowed the publication. One of the characters in the dialogue was named Simplicius. and it was he who upheld the Ptolemaic system. Some ignorant priests represented to the Pope that Simplicius was meant to represent himself and hold him up to ridicule. Orders were then given for the seizure of every copy of the book which was condemned as heretical. The Pope ordered Galileo to appear before the Inquisition at Rome. Being 69 years of age, he begged to be excused from the journey. But Urban, acting in much the same hard-hearted manner as the King of Denmark had acted towards Tycho Brahe, was enraged and said that the command must not be disobeyed. In February 1633, Galileo arrived in Rome, and 4 months later was tried before the Inquisition for teaching the Copernican system. On June 22nd, he was compelled to kneel before the cardinals of the Roman Church, and with threats of death was ordered to declare that he would in future detest the false opinion that the sun was the center of the universe and that the earth moved. Rising from his knees, tradition says he whispered to one standing near him, "Y pur si mueve," for all this it does move. Galileo was sentenced to be imprisoned as long as Pope Urban desired. His health, however, suffered from the intense heat at Rome, and he was allowed to return to his house at Arcetri near Florence, in which he was commanded to remain in everlasting solitude. At last came the tragedy at the end of his life. His sight began to fail, and in the end of 1637 he became totally blind. On January 2, 1638, he wrote thus to a friend, "Alas, your dear friend and servant Galileo has been for the last month perfectly blind, so that this heaven, this earth, this universe, which with wonderful observations I had enlarged 100, 1,000 times beyond the belief of bygone ages, henceforth for me is shrunk into the narrow space which I myself fill in it. So it pleases God, it shall therefore please me also." Galileo died at Arcetri on January 8, 1642, aged 77, having been blind for 4 years. Even after he was dead, the Pope would not allow a monument to be erected to his memory. Still, despite the foolish attempt to crush the Copernican system, Galileo, though he died in misery, was in the end triumphant. While Galileo was confirming the Copernican theory by observation, another great man was confirming it by mathematics. By means of difficult calculations, he made discoveries as brilliant as Galileo made with the telescope, and his calculations, which were based on Tycho Brahe's observations at Uraniaborg, finally led to Newton's discovery of universal gravitation. The name of this man was Johann Kepler. He was born at Wilderstadt in the Duchy of Württemberg in Germany in 1571, and was thus the first of those great German astronomers to whom science has owed so much. Kepler was the son of a soldier, and his grandfather was the burgomaster of Wilderstadt. Kepler, who was always in very poor circumstances, was educated at the school of Melbourne, which was preparatory to the University of Tübingen. At length, when he was 17 years of age, he entered the University of Tübingen and learned from Maestlin, the professor of mathematics there, that the Copernican theory was the true one. When Kepler left the university, he was without means and had no prospect of employment. Shortly afterwards, however, the professorship of astronomy at Graz fell vacant through the death of the professor, and Kepler, who as yet had no special inclination for astronomy, was offered it, and urged by his friends to accept it, which he did with considerable reluctance. He was then 23 years of age. It was while he was at Graz that Kepler hit upon a theory which, though long since discarded, was very ingenious. He considered that the 5 regular solid figures, known to mathematicians, corresponded with the 5 planets, Mercury, Venus, Mars, Jupiter, and Saturn. The idea was a daring one, but is now absolutely useless. All the same, it made Kepler prominent in the world of science. He wrote a book advocating it, and by means of this book he became known to Tycho Brahe and Galileo. As the inhabitants of the Graz were chiefly Roman Catholics, all the Protestant professors were expelled in 1599, Kepler among them. But he had now become a famous man of science, and he was restored to his position. However, he had no pupils, and he was glad in 1600 to accept the post of assistant to Tycho Brahe near Prague. When Tycho Brahe was dying in 1601, he requested Kepler to use his observations, which had been collected at Uraniaborg from 1577 to 1597, believing that by means of these observations the true system of the universe would at last be revealed. After Tycho's death, Kepler was appointed to succeed him as imperial mathematician to Emperor Rudolf. He was promised a handsome salary in his new post, but it was never paid. Tycho expressed the wish that the observations might be continued after his death, but this wish was not to be fulfilled. Kepler, faithful to the last wishes of the Danish astronomer, commenced to observe Mars with the great telescopes which Tycho had brought from Uraniaborg. In 1602, however, Tycho's son-in-law, Nagel, who pretended to be interested in astronomy and was jealous of Kepler, deprived him of the instruments and promised the Emperor Rudolf that the planetary tables would be finished within 4 years. Kepler never saw the instruments again, as they were stored away in an old vault, and they were probably destroyed in the Bohemian Rebellion of 1619. As to the observations of Tycho, Kepler at last got to access them, and Nagel soon abandoned the idea of working at the Rudolphine tables, which now occupied the attention of Kepler. As has been already mentioned, Kepler's promised salary was never paid, and for years he was, as he himself remarked, begging his bread from the emperor. Owing to his poverty, he was unable to publish the Rudolphine tables for about 20 years. Sometime after the death of Tycho, Kepler published a book on comets. In 1609 he published Commentaries on the Motions of Mars, the work which contained the first of the 3 laws of planetary motion, which showed that the planets revolved round the sun in elliptical orbits. Kepler could not reconcile the observations of Tycho with the theory of circular orbits. There was not a very large difference, and many men would have accounted for the differences by the supposition that Tycho had made a mistake, and would thus have lost the chance of making a great discovery. But Kepler knew Tycho Brahe, and he was certain that the great astronomer could not have made so large an error. Kepler's second law was published in a few years after the first. The irregularities in the motions of the planets were now accounted for, and the great laws of Kepler removed the difficulties which stood in the way of the acceptance of the Copernican system, and confirmed it as conclusively as did the telescopic observations of Galileo. The observations of Tycho Brahe confirmed the system of Copernicus, which he himself had rejected. Kepler was still in extremely poor circumstances, and accordingly he asked the emperor to pay his salary. Rudolf ordered it to be paid, but the Bohemian exchequer was empty. In 1610, the year of Galileo's great telescopic discoveries, Kepler suffered almost every sorrow imaginable. He was in great poverty. The Austrian troops occupied Prague, his wife died, and his favorite son also died. He went to Austria to secure a professorship at Linz, but Rudolf would not allow him to leave Prague, and promised to pay his salary, but again failed to keep his promise. At this time Kepler was in such extreme poverty that he was compelled to write what he called a vile prophesying almanac, filled with astrology in which he did not believe. It has been pointed out as remarkable that the world would not give him bread for his astronomical discoveries, but it would give him money for what he knew to be lies. Rudolf died in 1612, and the new emperor Matthias, his brother, allowed the astronomer to accept the professorship at Linz, and asked him also to retain the position at Prague. During all his misfortunes, Kepler exhibited a beautiful nature. In January 1610, the satellites of Jupiter were discovered by Galileo. Kepler was the only man who accepted the discovery without hesitation, even though it ran counter to his ideas of the 5 regular solids. He welcomed the news of his friend's success. A follower of Kepler attacked Galileo, accusing him of having plagiarized some of the former's discoveries, for which Kepler compelled the man to apologize to the Italian astronomer. Another instance of his fine nature can be given. One of his rejected theories, writes one of his biographers, assumed a new planet between Mars and Jupiter. Kepler was afraid that this might be mistaken by a careless reader to be an anticipation of Galileo's discovery of the satellites of Jupiter, and so in a subsequent edition of his work, The Five Regular Solids, published in 1621, he adds a note referring to his supposed planet. Not circulating round Jupiter like the median stars, be not deceived. I never had them in my thoughts. Before leaving this subject, it may be noted that Kepler's prediction of a planet between Mars and Jupiter was, as we have seen, confirmed by the discovery of the early asteroids by Piazzi and Aubers 100 years ago. Kepler was soon expelled from Linz on account of his Protestantism. He refused in 1617 to accept a professorship at Bologna with a large salary. In 1619 he published his third law in a work entitled The Harmonies of the World, dedicated to King James VI of Scotland. The discovery of this law was the aim of his life. In 1622 he wrote Epitome of the Copernican Astronomy, defending the Copernican system. The book was at once prohibited by the Church of Rome. At last, in 1621, the Rudolphine Tables, the result of the labors of Tycho Brahe, were published, and in recognition of this work and of his services to astronomy, Kepler received a gold chain from the Grand Duke of Tuscany. In 1620 a proposal was made to Kepler that he should leave Germany and go to England, but he declined to leave his native country. When Kepler was 57 years of age, he received an offer to live under the protection of the Duke of Friedland. A professorship at Rostock was also given to the great astronomer, and his future career seemed hopeful. Before leaving Bohemia, however, he made a journey to Ratisbon to procure the salary which had never been paid to him. But anxiety about the payment of his money proved too much for him. His health, always delicate, gave way, and while at Ratisbon he was seized with illness and died in 1630. He was buried in St. Peter's Church in Ratisbon, where 100 years ago a great statue was erected to his memory. The last of the great astronomers before Newton was Huygens, the Dutch scientist. Huygens was born at The Hague in 1629. He was the second son of the Dutch poet, Constantine Huygens, counselor to the Prince of Orange. When he was 13 years of age, Huygens began to take much interest in mathematical studies and examined every piece of machinery he could lay hold of. He was educated at the University of Leyden and was, like Tycho Brahe, intended to study law, for which he was sent to Breda. But the bent of his mind was towards science, and when he was 24 years of age, he wrote some treatises on geometry, studying that subject until 1651, when he devoted himself to observational astronomy. Since the death of Galileo, the founder of telescopic observation, there had been little improvement in the making of telescopes, and no further discoveries had been made in the celestial regions. The mystery of Saturn, which puzzled Galileo, remained a mystery. Nothing was known regarding nebulae, while, with the exception of Galileo's discoveries of the Martian phases and a few observations by Fontana at Naples in 1636 and 1638, the study of the planet Mars had not yet been begun. In fact, until Huygens arrived upon the scene, telescopic observation remained a standstill. In 1655, Huygens, with the help of his brother, set about telescope making. By a new method he ground and polished lenses which were much more powerful and much more perfect than those used by Galileo. Huygens then commenced to observe the planet Saturn in order to solve the mystery of its elliptical appearance. As mentioned in a previous chapter, the famous ring of Saturn was detected by Huygens. He was also the first to study nebulae. On June 16, 1659, he presented the first pendulum clock to the States General of Holland, the invention being the result of accurate astronomical observations. Huygens, in 1660, visited England, where he solved some problems in mathematics. He left Holland in 1665 and settled in Paris at the invitation of Louis XIV. In France, he devoted himself to other researches beside astronomy and mathematics. Like his illustrious contemporary Newton, he speculated in chemistry and discovered the true nature of light, which perhaps forms the boundary line between astronomy and chemistry. He found that light travels through space in the form of waves, a view which did not command universal acceptance until about 100 years ago, when it was revived and established. Huygens remained in Paris until 1681, when the persecution of the Protestants compelled him to return to Holland. Here he continued his astronomical observations. He constructed telescopes of enormous length known as aerial telescopes, and 3 of his object glasses are still in the possession of the Royal Society. He invented an almost perfect eyepiece known as the Huygenian eyepiece, which is still extensively used. It is also interesting to know that Huygens was one of the strongest supporters of the theory of life on other worlds. In his work Cosmotheros, published at The Hague in 1698, shortly after his death, he speculated regarding the possible inhabitants of the planets and brought forward arguments in favor of the plurality of the worlds. Unfortunately, Huygens did not accept Newton's view that gravitation was universal, although he admitted that it regulated the movements of the planets. It was with considerable difficulty that he could accept the views of others, but it has been pointed out that this was not due to an unwillingness to acknowledge the merits of his contemporaries. He was unable to depart from his own methods. It may be noted that Newton rejected 2 of Huygens' theories, one of these being the nature of light. Huygens died at The Hague in 1695 at the age of 66. His career closed an epoch in astronomy, which prepared the way for the work of the mightiest intellect which has ever applied itself to the problems of the heavens. End of Chapter 30.
Chapter 31 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 31. Newton and His Successors. The work of Kepler prepared the way for the greatest discovery ever made in the history of astronomy. In the first chapter, reference was briefly made to the marvelous fact of gravitation, but gravitation is never thought of or spoken of apart from its discoverer. It is, quote, the Newtonian law, end quote. It is never dissociated from the mighty intellect which first revealed it. Kepler had detected the laws of the planetary motions, but he was unable to show the cause of these motions. The hour had come for the discovery of the fundamental law of the universe, and with the hour came the man. Isaac Newton, the illustrious astronomer, was the son of a Lincolnshire farmer. Born at Woolsthorpe, near Grantham, in 1642, he was sent at the age of 12 to a school at Grantham. At first he was very idle in his studies, but it was not long before he began to take an interest in constructing mechanical models and sundials. One of these dials still remains at Woolsthorpe. When he was 14 years of age, Newton was removed from the school by his mother, who desired him to become a farmer, hoping that he would now lay aside his books and the studious habits to which he had become addicted. On one occasion, Newton was sent in company with an old farm servant to a neighboring town to sell the products of the farm. The young astronomer, however, preferred to leave the disposal of the products to his companion, and interested himself in a collection of old books which he had found in a garret. One of his uncles found him one day sitting behind a hedge reading a book on abstruse mathematics instead of attending to the farm. It was clear that he would not make a good farmer, and his mother, at his uncle's suggestion, wisely resolved to send him to the school to prepare for the university. On June 5, 1660, when he was 17 years of age, Newton entered the University of Cambridge, and soon afterwards finally turned to astronomy and mathematics. In 1664 and 1665, his excessive study of mathematics brought on ill health, which was intensified by sitting up at night to observe a comet. He made such progress in his studies that in 1669, when in his 27th year, he was appointed Lucasian Professor of Mathematics at Cambridge. Among Newton's early studies were his investigations on light. He was much interested in it, and was the first to disperse it in a prism. He showed that white light was actually composed of the 7 colors: red, yellow, orange, green, blue, indigo, and violet. But he could never have foreseen the discoveries made in the 19th century. He formulated a theory of light opposed to the true view of Huygens, supposing light to be caused by the emission of minute particles from the celestial bodies. He was so great a man in comparison with Huygens that his theory was believed for over 100 years. Isaac Newton's researches regarding light prepared the way for the invention of the reflecting telescope. Galileo, as already mentioned, was the first to invent the refractor. It was soon found that as the size of the instrument was increased, the field of view was impaired by a defect known as chromatic aberration. In fact, the object glasses, like prisms, dispersed the light into its primary colors. To counterbalance this difficulty, Huygens and Hevelius made telescopes of enormous focal length. But this could not go on forever, and Newton, in his investigations on the subject, came to the conclusion that it was impossible to produce a telescope which would be free from chromatic aberration. We know that he was wrong, as several English opticians afterwards succeeded in constructing telescopes free from this defect, and known as achromatic refractors. Perhaps, however, it was as well for astronomy that Newton erred in regard to the telescope. He determined to make a telescope which did not depend upon refraction, and constructed a concave mirror by a combination of copper and tin, which shone with the luster of silver. He then fixed it at the bottom of a tube, and the images of the stars were examined by means of a magnifying eyepiece. The little telescope was only 1 inch in diameter, but all the same it distinctly showed the satellites of Jupiter and the faces of Venus. It is now preserved by the Royal Society of London in memory of the great astronomer. This invention was an invaluable boon to science, and gigantic reflectors have since been constructed on Newton's principle by Herschel, Ross, and other eminent astronomers. In 1666, as previously mentioned, he began his investigations of the subject of gravitation. Whether the well-known story of the apple is true or not, it is an excellent illustration of Newton's line of reasoning. The story is that in 1666, as Newton was sitting in his garden at Woolsthorpe, the fall of an apple led him to ask if gravitation, already known to exist on the Earth, and which caused the apple to fall, did not also hold the moon to the Earth. The great discovery was made. Having extended gravitation to the moon, the great astronomer could likewise extend it to the solar system. By this method, the laws of Kepler were shown to be the natural outcome of universal gravitation. All this may seem very simple, but a great number of difficulties lay before Newton. He could not reconcile several facts regarding the moon with the theory of gravitation, and he abandoned the subject until 1684. At that time, a discussion was proceeding in London between the astronomer Halley, the scientist Hooke, and the architect Sir Christopher Wren regarding the movement of a planet according to gravitation. Hooke, who was a jealous and vain man, tried to make people believe that he had the solution, but would not give it to the world until, by attempting, people had found out how difficult it was, and would thereby honor the discoverer. Halley, in order to get more light on the subject, asked Newton, who, to his surprise, solved it at once. Halley urged Newton to publish his discoveries regarding universal gravitation. At that time also, new measurements regarding the moon's distance had removed the difficulties which had hindered the establishment of the law of gravitation. Newton therefore published his discoveries in the great work The Principia, which was given to the world in 1687. In this work, he showed the tides also to be the outcome of gravitation. In fact, he announced the great law that, quote, every particle of matter in the universe attracts every other particle, end quote. This discovery was not, however, at once accepted. Huygens rejected it, though admitting that gravitation ruled the planetary motions. The clergy pronounced it to be impious, and it was a long time before it was taught in the universities. Still, like all true theories, it triumphed. It happened that Newton was not a rich man, and was unable to pay for the publication of the Principia. The Royal Society was also without available funds, and the result was that Halley generously had the book published at his own expense. Halley was Newton's most devoted friend, and their friendship continued without interruption. After the publication of his book, Newton speculated in chemistry, but all his labors were lost by an unfortunate accident. One morning he went to church, leaving a lighted candle among the papers on his desk. It is said that his pet dog, Diamond, upset the candle. When the astronomer came home, he found all his papers destroyed. He exclaimed, quote, "O Diamond, Diamond, thou little knowest the mischief thou hast done." End quote. His health was impaired by the accident, and though only about 50 years old at the time, he made no more great discoveries. In 1687, Newton came prominently before the public. In that year, when James II attempted to infringe on the rights of the University of Cambridge, Newton was one of the 9 men who defended the conduct of the university and won the case. In 1688, he represented the university in Parliament, and for 2 years retained his seat. At length, many of his friends began to think that he should get some honor or appointment. Mr. Charles Montague, a great friend of Newton, was appointed Chancellor of the Exchequer in 1694, and in 1695 he offered the position of Warden of the Mint to the astronomer, who accepted it, his knowledge of physics being of much use to him in his new sphere. In 1697 the position of Master of the Mint fell vacant, and Newton was appointed to that office. He soon found, however, that he could not discharge his duties both at the Mint and at Cambridge, and in 1701 he resigned his professorship and severed his connection with the university. In 1703 Newton was elected President of the Royal Society, a position which he held until the end of his life. In 1705 he was knighted by Queen Anne in recognition of his great discoveries. He now resided in London, and during the remaining years of his life he was chiefly occupied with his duties at the Mint and at the Royal Society, and his mathematical and theological studies. He was deeply interested in theology, being of an extremely religious temperament. On March 20th, 1727, Sir Isaac Newton died in London, after a long illness, at the age of 84. A week later he was buried in Westminster Abbey. A magnificent statue was afterwards erected to his memory at Cambridge, where he is represented as holding in his hand a prism. Another memorial to England's greatest astronomer was erected in Lincolnshire in 1858. Considering the vast importance of his discoveries, Sir Isaac Newton was in no way elated. He was always ready to acknowledge what he owed to the great men who preceded him. "If I have seen farther than other men," he said, "it is because I have stood on the shoulders of the giants." His prevailing humility is well expressed by him in his old age, when he compared himself to a little child on the seashore gathering pebbles. He had picked 1 or 2 from the waves, but the infinite treasures remained undiscovered. Newton's chief contemporaries, Flamsteed and Halley, were the first and second holders of the office of Astronomer Royal of England. Both were distinguished men. Flamsteed was the elder of the two, and like Hipparchus and Tycho, was essentially a practical astronomer. His star catalogue, constructed at Greenwich, is a standard work, and has been for many years a book of reference to astronomers all over the world. Flamsteed died in 1719, after a life of usefulness and activity. Halley, who succeeded him, was more of a brilliant genius, and less of a steady observer than Flamsteed. Born in 1656, he was the son of Edmund Halley, a wealthy soap boiler in London. Young Halley from his earliest years showed interest in mechanical invention. He was educated at St. Paul's School in London, and by the time he left the school, he had made much progress in astronomy and mathematics. At the age of 17, he entered the University of Oxford. At this time, he was deeply interested in mathematics, and solved some questions regarding movement in an ellipse, and at the age of 19, he published a mathematical treatise. Halley had no intention of being merely an astronomer on paper. He longed to start the practical work of observing. This was an easy matter, for not only was his father wealthy, but he was a wise man, and was anxious that his son should take up the subject in which he was most interested. He therefore gave him an allowance of £300. The young astronomer desired to follow Tycho Brahe's example in determining the positions of the stars with great accuracy. Finding, however, that Flamsteed of Greenwich and Hevelius of Danzig were engaged on work of the same kind, he determined to visit the island of St. Helena to observe the southern stars, which until then had been neglected. Halley left Oxford University before taking his degree, and set sail in 1676, when in his 20th year, in an East India Company ship. 3 months later he arrived at St. Helena, having with him a sextant and a telescope 24 feet in focal length. The climate of the island, however, proving unfavorable, Halley remained for 1 year only. All the same, he accomplished much valuable work, which gained for him the title, quote, "Our Southern Tycho." End quote. In 1677 the astronomer returned to England, and through the influence of King Charles II, he was made a Master of Arts at Oxford in the following year. In 1678 he was elected a Fellow of the Royal Society, and some time later he was appointed Secretary, an office which he held until he was made Astronomer Royal. In 1679, he visited Germany in order to represent the Royal Society in a controversy with Hevelius of Danzig in regard to the utility of the telescope in the determination of the positions of the stars. Halley remained at Danzig with Hevelius for a year, and spoke highly of Hevelius's skill as an observer. In 1680, Halley traveled over Europe. He spent much time at the Paris Observatory, at that time directed by Cassini, famous for his satellite discoveries. Halley and Cassini made observations together on the comet of 1680. The English astronomer was very well received in Paris and in all the continental cities. Halley was much interested in the subject of magnetism and the variation of the magnetic needle. In 1692 he put forward a theory of terrestrial magnetism. Twice he took a voyage to the southern seas to observe this variation. In 1694 he set out, but he was obliged to return in 1695 as one of his lieutenants mutinied. In 1699 he again set out and passed the 52nd degree of latitude. In these latitudes, he said, we fell in with great islands of ice of so incredible height and magnitude that I scarce dare write my thoughts of it. The ice preventing his advance, he finally returned to England in 1700 and published a chart respecting magnetic variation. In 1684, Halley became intimate with Newton, and indeed it was he who advised Newton to publish his discoveries in regard to gravitation. In December 1684, Halley announced to the Royal Society that Newton was about to write a paper on the subject of gravitation. As has already been explained, the Royal Society was at a very low ebb in regard to funds. At length the Society ordered that Halley, quote, should undertake the business of looking after the book and printing it at his own charge, end quote, which he agreed to do. Reference has been made in the chapters on comets to Halley's greatest discovery, that of the revolution of the comet bearing his name. Another of his great discoveries related to the transit of Venus. He saw that the transits would give astronomers an opportunity of measuring the distance of the sun from the earth, and he urged on astronomers the necessity of observing the transit of 1761, which, however, he knew could not occur until many years after his death. His advice was taken by other eminent astronomers who followed him. In 1715, Halley observed the total eclipse of that year, the first which was visible in London since 1140. He observed the eclipse from the rooms of the Royal Society, and left a minute description of the corona. The death of Flamsteed, which took place in 1719, gave Halley the position of Astronomer Royal, to which he was appointed in 1720. He found no instruments in the observatory at Greenwich, as those hitherto in use, being the property of Flamsteed, had been removed by his wife, who refused to sell them to Halley on account of unhappy differences which existed between the two astronomers. Not only had Halley no instruments, but he was also without assistants. In 1721 he had a telescope erected at Greenwich, and then, though 64 years of age, he determined to observe the moon during a period of 18 years. Halley just lived to complete his observations, which were very useful. His health began to give way in 1739, and he died in 1742, at the age of 85, having survived Newton for 15 years. He was buried at Lee, in Kent. James Bradley and James Ferguson, the remaining two men of note among Newton's immediate successors, were each men of distinction in their particular spheres. James Bradley was born at Sherborne in Gloucestershire in 1693. Of his private life there is little to tell. He was educated first at the School of Northleach and afterwards at the University of Oxford, which he entered in 1711, when in his 19th year. While at the university, he spent much time with his uncle, the Reverend James Pound, who, although by profession a clergyman, was deeply interested in astronomy and a well-known observer. It was doubtless through friendship with his uncle that Bradley became expert in the use of astronomical instruments. Bradley and his uncle together investigated the subject of the parallax of the Sun by observing the opposition of Mars. Pound and Bradley showed, as they believed, that the distance of the Sun must be more than 94 millions of miles and less than 125 millions. We now know that they overestimated the Sun's distance. But considering their imperfect instruments, it was remarkably near the truth. Halley had evidently a high opinion of Bradley, whose talents were now so widely known that he was elected a Fellow of the Royal Society in 1718. About this time, Bradley paid much attention to the eclipses of Jupiter's satellites, which he predicted with much accuracy. Bradley was originally intended for a clerical career, and in 1719 the Bishop of Hereford offered him the vicarage of Bridstow in Monmouthshire, to which he was appointed in 1720. But he was only 2 years in his clerical position. The civilian professorship of astronomy at Oxford, previously occupied by Halley, became vacant by the death of Halley's successor, Kyle. At that time, it was a rule that the civilian professor of astronomy must not hold a clerical appointment, and there is little doubt that Pound would have been elected had he been willing to surrender his connection with the church. Bradley, however, expressed his willingness to give up his vicarage, and he was appointed to the civilian chair in 1722, when he was 29 years of age. Notwithstanding the awkward and inconvenient instruments with which the civilian professor had to conduct his observations, in 1723 he observed the transit of Mercury and succeeded in measuring the size of Venus, while he made many important observations on the comet of 1723. The greatest of Bradley's discoveries was made in 1725 and 1726. He was looking for something quite different from what he discovered. From the time of Copernicus, astronomers had made every effort to measure the parallax of the stars, and their inability to do so was long felt as one drawback of the Copernican system. Bradley made an attempt. He was not successful, but his labors were rewarded by a brilliant discovery, that of the, quote, aberration of light, end quote. The astronomer decided to make observations for a year on the star Gamma Draconis in the constellation Draco, the instrument used being a refractor 24 feet 3 inches in focal length. It was erected in Kew Green, near London, at the house occupied by Samuel Molyneux, afterwards a Lord of the Admiralty, who at one time was greatly interested in astronomy. The observations in search of parallax were continued for a year. It was found, after much patient observation, that Gamma Draconis was actually displaced in position. But Bradley was not long in finding that the displacement was not due to parallax, as it was of an exactly opposite character. For a long time the astronomer was much perplexed as to the cause of the variation, and he determined to make elaborate investigation of various other stars. He found that all the stars which he observed showed the same displacement. This phenomenon was not explained by Bradley until some time after the remarkable discovery. It had been discovered before the time of Bradley, by Roemer, that light requires time to travel through space, and it was found that the rate at which it traveled was 186,000 miles a second. Bradley then hit upon the idea that the reason of the displacement was the combined movements of light and the Earth. Thus, as the Earth moved, the stars were displaced in position. This discovery finally confirmed the Copernican theory by showing that the Earth really moved, and it was also of great use in astronomy. Bradley made many experiments to verify his discovery, which was soon placed beyond all doubt. This discovery gained for Bradley the admiration of Newton, who, in his old age, was heard to call him, quote, the best astronomer in Europe, end quote. In February 1742, Bradley was appointed Astronomer Royal of England in succession to Halley. In June 1742, he made his first observation with the transit instrument at Greenwich. The new Astronomer Royal was an extremely energetic man, and it appears that on one day, 255 observations were taken by himself alone. By 1747, he had completed the observations which revealed his second great discovery, that of the nutation of the Earth's axis. It had been known for long that the pole of the Earth is not fixed, and does not point constantly to the same point in the sky. Thus, the star in Ursa Major, which we call the pole star, will not occupy that position forever. In the course of 25,000 years, the pole will have moved in a great circle through the sky, and will once more point to the pole star. During its revolution in the course of 12,000 years, the pole will be close to Vega in Lyra. What Bradley discovered was that in the course of 19 years, the position of the pole varied in an extraordinary manner. This was at first thought to be inconsistent with Newton's theory, but Bradley showed it to be due to the variable action of the moon on the matter accumulated round the terrestrial equator. In 1752, Bradley took a prominent part in the change of the calendar in England. Many years before, the Gregorian calendar had been instituted by one of the popes and adopted by many of the countries of Europe. In this matter, the Roman Catholic Church happened to be right, but England for long refused to accept the new calendar. For his efforts, Bradley met with violent opposition. In the words of Mr. Morton, quote, the people believed that the astronomer was somehow going to rob them of 11 days of their lives, and his decline and death soon after was popularly supposed to be the judgment of heaven, end quote. During the last 2 years of his life, he was subject to a melancholy depression, as he feared that he would survive his mental powers. Probably this depression hastened his death, which took place in 1762. Newton's theory of gravitation, despite his work and that of his successors, was not at first popular, especially in England. Strange to say, England was not the first country to accept the Newtonian teaching. In Scotland, the law of gravitation was taught earlier than in the sister kingdom, and indeed it fell to a Scotsman to popularize fully the Newtonian theory. Quote, astronomy explained upon Sir Isaac Newton's principles, end quote, was the work of James Ferguson. James Ferguson was born at Cor of Mayenne, near Rothieme in Banffshire, in 1710. His father, John Ferguson, was a poor farm laborer, and James was the second son. The future astronomer had little education. He learned to read unaided, and his father, a man of considerable intelligence, taught him to write. About 3 months I afterwards had at the grammar school at Keith, wrote Ferguson, was all the education I ever received. When about 7 years of age, he became interested in mechanics and wrote an account of mechanical contrivances. At the age of 10, he was sent by his father to keep sheep for a neighbor. While so employed, he began to study the stars. When he was 14 years of age, he, to give his own account, quote, went to serve a considerable farmer in the neighborhood, whose name was James Glashand. I found him very kind and indulgent, but he soon observed that, when my work was over, I went into a field with a blanket about me, lay down on my back, and stretched a thread with small beads on it at arm's length between my eye and the stars, sliding the beads upon it till they hid such and such stars from my eye, in order to take their apparent distance from one another, and then, laying the thread upon a paper, I marked the stars thereon by the beads according to their respective positions, having a candle by me. My master at first laughed at me, but when I explained my meaning to him, he encouraged me to go on, and that I might make fair copies in the daytime of what I had done in the night, He often worked for me himself." End quote. Thus, in the lonely hills of Banffshire, the shepherd boy astronomer, encouraged by this kindly farmer, commenced observation of the great orbs of heaven. Through Glashan, Ferguson became acquainted with higher people about Banffshire, and lived for a time with Thomas Grant, a neighboring gentleman, whose butler encouraged him in his studies. This man was evidently a good mathematician, and he taught Ferguson algebra and geometry. After his friend left the gentleman's house, Ferguson went back to live with his father, and was employed by a miller about 1731. In the following year, Ferguson became acquainted with Sir James Dunbar of Durn, whose sister, being much interested in the young astronomer, took him with her to Edinburgh in 1734. He remained some time in Edinburgh, and while paying a visit to Inverness in 1739, he again became interested in astronomy, and constructed on paper an elaborate diagram of the motions of the sun and moon. He also made calculations regarding eclipses of the sun. Ferguson returned to Edinburgh in 1741, and 2 years later finally quitted Scotland for London, taking along with him a mechanical orrery representing the movements of the planets, which he constructed in Edinburgh. On his arrival in London, the astronomer became intimate with a gentleman who proposed to get him appointed master of a mathematical school. The plan, however, collapsed, and Ferguson took up the business of drawing pictures and lecturing on astronomy. In the words of Henderson, the author of The Life of Ferguson, quote, "With these two professions, Ferguson had a somewhat severe struggle for a living in London for nearly 17 years." End quote. Although James Ferguson was a great observer, he was not a great mathematician, and to the end of his life he did not understand Euclid. He had, however, a genius for mechanical invention, and he constructed a large number of orreries, planetariums, etc., representing the motions of the sun, moon, planets, and comets. These mechanical models were highly complex in their structure, and we may assert that no astronomer has ever possessed such a genius for representing the movements of the celestial bodies by means of mechanical contrivances as James Ferguson. He likewise constructed astronomical clocks and sundials. In fact, everything connected with observational astronomy was dealt with in these wonderful machines. In 1748, Ferguson commenced his popular lectures, the first subject being the solar eclipse of July 14th in that year. The following year, he lectured on other subjects besides astronomy, including mechanics, electricity, optics, etc. In 1751, he constructed his satellite machine, which represented by clockwork the motions of Jupiter's satellites. An excellent illustration of this machine is given in Henderson's work, to which reference has already been made. Ferguson published in 1754 one of his works, quote, "An idea of the material universe from a survey of the solar system," end quote. And at this time he was making preparations for his greatest book, quote, "Astronomy explained upon Sir Isaac Newton's principles," end quote, which was published in London in June 1756. During the author's lifetime, it went through 6 editions. Ferguson was now held in universal respect, and his work superseded for a great number of years all other books on astronomy. But he was in very poor circumstances, his sole livelihood being picture drawing and his lectures. In 1760, King George III granted to Ferguson an allowance of £50 a year. This pension was given at a critical period in the astronomer's life, when his difficulties almost made him contemplate returning to Scotland. The pension, however, placed him in a fairly prosperous position, and he lectured at Bristol and at Bath with great popular success. His reputation, too, increased, and in 1763 he was elected a Fellow of the Royal Society. In 1761, Ferguson observed the transit of Venus from the top of the British Museum, using a 6-foot reflector. He remarked, quote, "I carefully examined the sun's disk to discover a satellite of Venus, but saw none." End quote. For some time before the transit, he had been taking much interest in it, as it afforded the best means of measuring the sun's distance. 2 years later, he sent a paper on his observations to be read before the Royal Society. Year after year, the astronomer invented new machines representing the movement of the planets to be exhibited at his public lectures. He also observed the spots on the sun and left a drawing of them, while in 1769 he published a description of the transit of Venus of that year, the last of the pair of transits visible during his lifetime. Ferguson died in London in 1776. His name will forever be remembered as one who not only made important observations and constructed extraordinary instruments and machines, but as one who did more to make astronomy popular than any other astronomer of his day. The greatest service, however, which this man of science rendered was that it was his book on astronomy which started William Herschel on his wonderful career as an observer of the heavens, and for this alone the world can never be sufficiently grateful. But the chief lesson which we learn from the life of James Ferguson is that enthusiasm and perseverance overcome all obstacles. It is surely a striking fact that in the face of tremendous difficulties, the humble shepherd boy was destined to do more in popularizing astronomy than all his predecessors. End of Chapter 31.
Chapter 32 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 32. The Conquest of the Stars. In the foregoing pages, many references have been made to the immortal name of William Herschel, but little has been said of the exact position which Herschel occupies in astronomy. The astronomers before Herschel occupied themselves only with the solar system, the little group of planets moving around the sun. Even the mighty mind of Newton was obliged to concentrate on the solar system. The stars were observed certainly, but more as convenient reference points for the observation of the moon and planets than from the desire of the astronomers to learn anything of the stellar orbs for their own sake. It was reserved for Herschel to commence the conquest of the stars, to start astronomy on a new path. His epitaph claims that he broke through the barriers of the skies, and it is no exaggeration to say that this is true. He stands only second to Newton among the pioneers of astronomy, for he led his fellow astronomers, we might say, to a higher pinnacle of knowledge than had ever before been attained, and revealed a vista of infinity and eternity unthinkable to the mind of man. Herschel was born at Hanover on November 15, 1738. He was the third son and fourth child of Isaac Herschel, originally a bandsman, but afterwards the band member of the Hanoverian Guards. Although in humble circumstances, Isaac Herschel was a man of considerable intelligence, an eminent musician, and greatly interested in astronomy. He had a family of 10 children, and of these, William was by far the most accomplished. He and his sister Caroline, who was 12 years his junior, were the only members of the family who achieved distinction. From the beginning of her life, Caroline was deeply attached to her father and her brother William, who were the only 2 members of the family who showed her invariable affection. William Herschel attended the garrison school at Hanover until he was 14 years of age. Here he displayed his love of learning and his brilliant powers by mastering his lessons in half the time taken by his brother Jacob, his senior by 4 years. William Herschel was a competent musician and, along with his brother, became an oboist in the Hanoverian Guards, of which his father was bandmaster. The outbreak of the 7 Years' War in 1756 compelled the Hanoverian Guards to fight. Conscription being the rule, the musicians were not exempt from serving their country. After the defeat of the English and the Hanoverians at Hastenbeck in 1757, William Herschel spent the night in a ditch, and, after due consideration, decided that fighting would not be his profession. In fact, with the consent of his father and mother, he deserted and sailed for England, where he arrived when in his 19th year. For some time he wandered through England in search of some musical employment, and in 1760 he was appointed to train the band of the Durham Militia. 5 years later he became organist at Halifax, and in 1767 in the Octagon Chapel at Bath, where he continued until he became an astronomer. Herschel in 1764 paid a visit to his father, who was now failing, and who died in 1767. His death was a severe blow to Caroline, whose affection was concentrated on her father and her brother William. Her father had desired to give her a good education, but her mother and her brother Jacob wished her to learn no more than was necessary for the education of a housemaid. After 5 years, William Herschel decided to take his sister with him to England, and she arrived in Bath in August 1772. At the time when Caroline Herschel arrived in England, her brother was beginning to take a deep interest in astronomy. After conducting a concert, Herschel would return to his room and study Maclaurin's fluxions and Ferguson's astronomy. His original interest in the latter science was due to his father, but the perusal of the work of Ferguson aroused a fresh desire to see for himself the orbs of heaven. As Caroline expressed it, "It soon appeared that my brother was not contented with knowing what former observers had seen. He hired a small telescope, and was so charmed with the wonders of the heavens that he determined to have an instrument for himself. He therefore wrote to London to make inquiries. But the price of the telescope was too great for Herschel with his limited means. The Bath musicians, however, was not the man to be baffled by difficulties. He made up his mind to make his own telescope, and, buying the apparatus of a local optician, he succeeded in constructing, after many failures, a reflector, the mirror of speculum metal. On his return from a concert, he would plunge with enthusiasm into telescope making, and, while grinding and shaping the mirror, he was obliged to hold his hands on it for 16 hours at a time, his meals being supplied by his sister, who also read stories to him to break the monotony. But for Caroline Herschel, who spared no trouble for her brother, William would have never become the famous astronomer, and she sacrificed for his sake her prospects as a public singer. In 1774, when he was 35 years of age, Herschel began to observe the heavens with his own telescope. For 7 years, Herschel maintained his love for astronomy while perusing the profession of music. Night after night, he swept the skies with various telescopes. Having made one instrument, he determined on seeing more of the celestial wonders and constructed larger ones. In 1779, through the friendship of Dr. Watson, an eminent literary man, Herschel entered the Literary Society of Bath. In the following year, he sent 2 papers to the Royal Society, followed by another in January 1781. But an event took place which completely changed the current of his life. In 1780, he began a review of the heavens with a 6-inch Newtonian reflector. As he explored the constellation Gemini on the night of March 13, 1781, he observed an object which, unlike the stars, showed a round and well-defined disk, the motion of which was quite perceptible. This discovery of the planet Uranus, mentioned in a previous chapter, was the occasion of much excitement. The Bath musician was at once raised to the rank of an illustrious astronomer. King George III, hearing of Herschel's discovery, summoned him to London in 1782 and conferred on him the title of King's Astronomer, with a small salary of £200 a year. The king, likewise, pardoned him for his desertion from the army 25 years previously. Herschel now cut himself adrift from the profession of music, and he and his sister settled at Datchet, near Windsor, in August 1782. He was then 44 years of age. William and Caroline Herschel removed in 1786 to Slough, near Windsor, "the spot of all the world," wrote Arago, "where the greatest number of discoveries have been made," and the astronomer remained there for the rest of his life. From dusk to dawn he swept the heavens with his mighty reflectors, in the mirrors of which the stars appear to move in a glorious procession. He discovered many star clusters, over 2,000 nebulae, and about 70 million stars. In 1787, Caroline Herschel was appointed his assistant with a salary of £50 a year. She would sit beside her brother, who would dictate to her what he saw. Sometimes, she tells us in her memoirs, the ink froze in her pen. Miss Clerk thus describes Herschel's enthusiasm. The thermometer might descend below 0, ink might freeze, mirrors might crack, but provided the stars shone, he and his sister worked on from dusk till dawn. While Herschel was thus rapidly rising into fame, wrote Mr. Syme in his admirable biography of the great German astronomer, he was not forgetful of the sister who so generously sacrificed her own wishes and prospects as a singer to advance his as an astronomer. He presented Caroline with a 5-foot reflector, with which she explored the skies. She discovered a number of clusters and nebulae and detected 8 comets, one of which is now known as Encke's, between 1786 and 1797. Von Magellan, a foreign astronomer, reported in 1786 that the brother and sister were equally interested in astronomy. The University of Edinburgh conferred on Herschel in 1786 the degree of LL.D. In 1792, he received the Freedom of Glasgow, and in 1816, he was created a Knight of the Royal Hanoverian Guelphic Order. 5 years later, he became the first president of the Royal Astronomical Society. But he cared little or nothing for honors. He was described as a man without a wish that had its object in the terrestrial globe. Like Newton, he was in no way elated with his wonderful discoveries. Writing to his sister from London in 1782, he said, "Among opticians and astronomers, nothing now is talked of but what they call my great discoveries. Alas, this shows how far they are behind, when such trifles as I have seen and done are called great." Advancing years in no way affected Herschel's wonderful mind, but his duties as king's astronomer necessitated his acting as what Mr. Syme calls showman of the heavens on the visits of royalties to Windsor, often after a whole day's work, when rest was absolutely necessary. This tremendous strain, which reflects little credit on the court, proved too much for the old man. His health began to give way, although his mind was as vigorous as ever. As Miss Clerk puts it, all his own instincts were still alive, only the bodily power to carry out their behests was gone. An unparalleled career of achievement left him unsatisfied with what he had done. His strong nerves were at last shattered. After a prolonged period of failing health, he died at Slough at the age of 83 on August 25, 1822. His sister survived him for 25 years, dying early in 1848 at the advanced age of 97. The son of the Hanover bandmaster was, in the truest sense, the founder of sidereal astronomy. He observed the suns which spangle the sky to discover the secrets of their constitution. He aroused, by his brilliant discoveries, widespread interest in the star depths. His career stimulated astronomical research during the 19th century. This may be seen from a study of the astronomical work of the past 100 years. The great work of Herschel has somewhat overshadowed his successors, many of whom have been men of the most brilliant genius. Contemporary with him were such men as Laplace and Olbers. Among his immediate successors, we find the great names of Bessel, Struve, and Henderson. In the middle of the century, Leverrier and Adams. While in more recent times, the astronomical army has been led to still greater triumphs by such men as Secchi, Huggins, and Vogel, Schiaparelli, and Newcomb, and many other devoted students of nature. Thus, while the romance of astronomy belongs in the first place to the heavenly bodies themselves, there is something no less romantic in the study of the labors of that noble band of men who have dared to sound the universe and conquer the unknown. End of chapter 32.
Chapter 33 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Larry Wilson. The Romance of Modern Astronomy by Hector Macpherson. Chapter 33. A Final Survey. In the preceding chapters we have dealt with the universe as we know it today, and with the means by which astronomers have reached their conclusions. The science of astronomy is in many ways the grandest of all the sciences, for it has enlarged our knowledge 1,000-fold, 1,000,000-fold, beyond all the other sciences. It leads us to look outwards by means of the telescope and the spectroscope into mighty vistas in space, and to look backwards in imagination over enormous vistas of time. Schiaparelli has called astronomy the science of infinity and eternity, and this phrase exactly describes the modern development of the science of the heavens. On all sides, the astronomer deals with the infinite and the eternal. The romance of modern astronomy consists in great part in the enormous extension of our knowledge of the visible universe. As a distinguished writer has well said, "Compared with the fields from which our stars fling us their light, the cosmos of the ancient world was but as a cabinet of brilliants, or rather a little jeweled cup found in the ocean of the wilderness." Wonderful as were the achievements and sagacious as were the guesses of the Greek astronomers, they little suspected what they were registering when they drew up their catalogues of stars. To the ancients the earth was the center of the universe, fixed and immovable, the end and aim of the entire creation. Round the earth revolved the moon, the sun, the planets, each in their own particular complicated pathways, and farther away the fixed stars, which they believed to be points of light fastened to the inside of a sphere. What lay beyond was outside the universe. The whole universe was supposed to be small in extent. Its size was quite easily grasped by the mind of man. The universe, too, in the opinion of the ancients, was created purely for the benefit of the earth's inhabitants, the sun to give light and heat, and the moon to illuminate the nights, while the stars were regarded as convenient secondary light givers in the absence of the moon. What a contrast between these views and the truths with which we are acquainted today with modern astronomy! So far from being the center of the universe, the earth is not even the center of the planetary system. So far from being the largest and most important body in the universe, it is merely what we might call the secondary satellite of a second-rate star. So far from the dimensions of the universe being conceivable, they are absolutely inconceivable. The solar system alone is nearly 5,000 millions of miles in diameter, and the solar system is a mere point in comparison with a greater system of stars. No less remarkable than the enlargement of the universe in space has been its enlargement in time. To the thinkers of the Middle Ages, a few thousand years contained the life history of the universe. Stars and suns were all brought into existence 6,000 years ago. Beyond, nothing was known. Modern astronomy has pushed back the beginnings of things into the vista of the past. Millions of years, tens of millions of years, take place of thousands. By observations on the heavens, by reasoning on these observations, astronomers trace processes which require millions of years for their completion. Astronomy is indeed the science of eternity. Not only so, it shows that there is in reality no such thing as time, that it is a purely relative conception, due to our position on a little planet revolving round a star. Our subject in the preceding pages has been the romance of modern astronomy, and nothing could have been more romantic than the steady development of our knowledge, till today we know the universe not as the little corner which it appeared to our forefathers, but as infinity itself. A brief survey may be taken of the journey which we have traversed in imagination in the preceding pages. Naturally, the mind of man in its journey through the infinite begins with the earth, our dwelling place. By the revelations of astronomy, we behold the earth as a globe, rotating rapidly on its own axis, and in ceaseless revolution round the sun, on whose beams it depends for its existence as an abode of life. At a distance of 238,000 miles, we come upon our faithful satellite, the moon, the only one of the celestial bodies which revolves round the earth. The moon is the earth's peculiar possession. As has been seen, it is a detached continent, probably literally as well as metaphorically. For we perceive, too, that the life of the moon as a world is long since ended. It is a closed chapter in the book of time. Modern astronomy shows us that, as Flammarion puts it, in space there are both cradles and tombs. The moon is one of the tombs of the universe. Then our study of the earth and moon shows that the earth and moon form by themselves a little system, the earth-moon system, or terrestrial system, as it is variously called, within the greater solar system. In the earth-moon system, Our scale of measurement is thousands of miles. In the solar system, we have to measure by a new scale, millions of miles. In the middle of the system, we see the mighty Sun, whose diameter is 100 times that of the Earth, rotating slowly on its axis and holding sway over a system of planets of all sizes, and in addition controlling the motions of the comets and meteoric systems. Examples have been given of the power of the Sun, of the storms raging in its atmosphere, of the sea of fire which surrounds it, and of the atmospheric catastrophes which give rise to the mighty spots or rents in the glowing atmosphere. Reasoning has shown us the enormous age of the Sun, that millions of years may elapse and make little change on the orb of day. So far as the inhabitants of the earth are concerned, the Sun is eternal. Round the Sun we see revolving the planets divided into the three well-defined groups. First we have the inner planets, of which our Earth holds the proud position of chief world, revolving at distances which vary from 36 millions to 141 millions of miles. This group includes swift little Mercury, whirling round the Sun with an enormous velocity, followed by Venus, then the Earth, and next Mars. Next we have the asteroids, the miniature worlds which fill the space between the pathways of Mars and Jupiter. Thirdly, we have the outer planets, revolving at distances varying from 484 millions to 2,700 millions of miles. Jupiter with its retinue of 8 satellites, Saturn with its more wonderful system of 10 attendant worlds and 3 revolving rings, Uranus with its 4 moons creeping along at a comparatively leisurely pace, and finally distant Neptune, the exile of the solar system, circling round the known boundaries of the solar system with one faint attendant. Across this enormous system, with a diameter of over 5,000 millions of miles, the rays of light flash in 8 hours. How vast is the system, how unthinkable are its dimensions, how unfathomable its depths, and how wonderfully is it regulated by that divine ordinance of nature, the law of gravitation. To the mind of the ancient astronomers, a system so vast as we know the solar domain to be would have seemed infinity itself. They would have been unable to conceive so great a revelation of immensity. Yet when we come to study the stars, a new truth dawns on our minds, that just as the earth and moon form by themselves a little system within the greater solar system, so the solar system itself, containing many lesser systems, is also but a little system within a greater, the system of the stars. In the Earth-Moon system, the scale is thousands of miles. In dealing with the solar system, we are obliged to use a new scale, a scale of millions of miles. And when we come to consider the universe of the stars, this scale itself is quite inadequate. The scale is one of billions and hundreds of billions of miles. So too in regard to the motion of light, a second and a half is required for light to pass from the moon to the earth. The scale of light velocity for the Earth-Moon system is seconds. For the solar system, that scale is minutes and hours, and for the stellar system, years and centuries. In his Popular Astronomy, Flammarion brings home very vividly the isolation and minuteness of the solar system in the greater system of the stars. On a journey through space in imagination, the French astronomer writes, "The sun himself, with all his immense system, has sunk in the infinite night. On the wings of intersidereal comets, we have taken our flight towards the stars, the suns of space." Have we exactly measured, have we worthily realized the road passed over by our thoughts? The nearest star to us reigns at a distance of about 25 billions of miles. Out to that star, an immense desert surrounds us, the most profound, the darkest, and the most silent of solitudes. The solar system seems to us very vast. Relatively to the fixed stars, however, our whole system represents but an isolated family immediately surrounding us. A sphere as vast as the whole solar system would be reduced to the size of a simple point if it were transported to the distance of the nearest star. The space which extends between the solar system and the stars, and which separates the stars from each other, appears to be entirely void of visible matter, with the exception of nebulous fragments, cometary or meteoric, which circulate here and there in the immense void. 9,250 systems like ours would be contained in the space which isolates us from the nearest star. When we come to contemplate the system of the stars, to journey through it in imagination, we see our sun from a new point of view. It is merely a star moving through space, and carrying with it planets, satellites, and comets. All the stars are in motion, some rushing through space with almost inconceivable velocity, others moving at a slower pace, but all rushing onwards at a speed to which we on earth are quite unaccustomed. There are in the system of the stars, so far as we know, about 500 million stars. In addition to those bodies, modern astronomy has revealed to us thousands of the luminous masses known as nebulae, which form the materials out of which finished systems of suns and planets are wrought by the divine power in the course of ages. Then astronomy shows us the possible shape of the starry system. It tells us of the galaxy, that mighty region of clustering orbs, the equator of the starry globe, and it indicates that the starry system, like the solar system and the smaller satellite systems, is merely a system within a greater. But what that greater system consists of, and how far it extends, the mind of man cannot tell. Even of this mighty system of the stars itself, our knowledge is limited. We do not know whether or not it has a central body. We do not know the precise distance to which it extends. We only can say that the more distant stars of the Milky Way are placed at a distance so great that it is almost impossible to express them on the scale of miles. On the scale of light, we can estimate that the light rays which dart from the moon in a second and a half and cross the diameter of the solar system in 8 hours require thousands of years to span the mighty void. The romance of astronomy can guide us no further. On the threshold of a vaster system we pause, and only speculation and theory can take us beyond. But how vast a field of space has modern astronomy revealed to us! Eternity, says Flammarion, is the field of the eternal sower. Throughout space we behold stars and systems in every stage of evolution, nebulous masses, clustering stars, finished suns and systems, decrepit worlds, and finally dead and dark stars. The eternal purpose of evolution is at work throughout the depths of space. The divine will is in constant operation while suns and systems are being fashioned, and nebulous matter being brought into new existence. What a vast and mighty universe modern astronomy reveals to the mind of man! A universe without bounds, without beginning or end in time, a universe in which the earth is but an absolutely insignificant atom, a globule lost in the infinite night. As Flammarion puts it, in the eternity of duration, the life of our proud humanity, with all its religious and political history, the whole life of our entire planet, is but the dream of a moment. It is at this point, the last of the great truths which we learn from the romance of astronomy, that the minds of many get disturbed. Some sigh for the old ideas of a compact universe and a history of a few thousand years, thinking it more conducive to religious faith. Others, by accepting these sublime truths, believe their faith shaken by the marvels which science has revealed. These attitudes are both mistaken ones. Although the romance of astronomy ends when the most distant star is reached, it has some bearing on the greater problem and the higher thought of men. Modern astronomy has revealed to us a universe infinitely vaster than was known to our forefathers. It has correspondingly widened and exalted our knowledge of the Creator of all things. Not only has modern astronomy done this, it has also shown the marvelous height which may be reached by the human mind, chained to a little revolving globule, lost in the rays of a star, yet able to span the vast spaces of the universe, to weigh the stars, to predict the celestial motions. It has given us a deeper appreciation of the dignity of the human intellect which can soar above its environment into the regions of things divine and eternal. We read much in the Bible of the infinite and the eternal, chiefly as attributes of God. Astronomy gives us examples of infinity and eternity, and leads us to a higher plane of thought and of religion. The romance of astronomy is more romantic than any romance, more fascinating than any story. By its means we are brought face to face with infinity and eternity, and after a study of the wonders which it reveals to us, we can only repeat with deeper reverence the words of the psalmist: "Thine, O Lord, is the greatness, and the power, and the glory, for all in heaven and earth is thine." End of chapter 33. End of the Romance of Modern Astronomy by Hector Macpherson.